and we have a modularity of characters, and you know the category of module as a natural fusion product. But there are cases outside this case when vertex operator algebra is quite nice. So one of the cases when this representation is so-called Katsuba-Kimoto admissible, and this is a case when the characters of this representation are modular invariant. Of course, integral representation, the character of integral representation are modular invariant, but there are much more cases than the integral representation when characters are modular invariant, and this case has a level, a fraction levels. And if this is the case, you can show that the corresponding associated variety is a closure of some nilpotent orbit in G star, and you can describe this orbit explicitly. And one of the nice reason that I consider such a variety is that it has a nice it has a nice compatibility with Drinfeld-Sokurov reduction. So if is a nilpotent element, you can define as corresponding the double algebra by taking a Drinfeld-Sokurov reduction. So this is a Drinfeld-Sokurov reduction. Of the universally affine vertex algebra, and depends on the your choice of nilpotent element or your choice of SL2 embedding. And it's known that the associated variety of the double algebra is the so-called slowed slice at F. It's a transversal slice to G orbit. And more generally, if you have a vertex operator algebra equipped with a vertex operator, a vertex algebra homomorphism from VKG to V, then this VOA has action of affine Lie algebra. So you can take Drinfeld-Sokurov reduction, and you get certain VOA. And so we'd like to think this homomorphism as a chiral momentum because it induces morphism from associated varieties, between associated varieties, and because associated variety of affine vertex algebra is G star, so you have a morphism like this, and this is indeed a moment map for the G action. So this kind of homomorphism can be regarded as affinization or chiralization of momentum. And a fact is that in this situation, associated variety of Drinfeld-Sokurov reduction of V is just a fiber, a product of the associated variety of V itself with a slowed slice, where the fiber product is taken corresponding to the moment map. And So in particular, if you take a Dirichlet-Sokolov reduction of the simple affine vertex algebra, you get just an intersection with associated variety of for the simple affine vertex algebra with the Schrodinger's slice, and which is so if K is admissible, this is a some nilpotent oblique closure. So you get the intersection of the nilpotent oblique closure with Schrodinger's slice. And so this kind of thing is called nilpotent Schrodinger's slice. And so this compatibility is quite useful in the study of representations of double algebras. So application to the representation theory of double algebra was my original motivation to study such varieties. But it turned out it's also useful in the so-called for the 2D correspondence. So let me go on to the 4D 2D correspondence by that is found by Bean, Demos, Liendo, Pilas, Rusty, and Van Ries. So they constructed a map from a 4-dimensional n equals to 2 superconformal field theories to the category of 2D chiral sheet conformal field theories, which can be identified with the category of vertex operator algebras. In such a way that we can compute the Schur index of for this theory as the character of the corresponding vertex operator algebra. And this is very nice because the Schur index is a very important invariant, and we can use representation theory of VOA to compute a Schur index. And so this functor or map is obtained by considering certain dimensional reduction. So you may think this loses many information of 4D theory. But it turned out this map is I understand that this map is injective in examples so far. So this is very nice invariant. And also it's not surjective because the image is never unitary. The reason is that we have this simple relation between center charge of 2D theory and 4D theory. So if you start with unitary theory, you end up with a negative center charge. So this cannot be unitary. So this means, in particular, this map is not a surjective. So the first statement that this V might be a complete invariant. So this VOA, if you know image of V, you know lots of information about 4D theory. And for people who work on vertex operator algebra, so this is very exciting as well, because for these theories is extremely rich theory, And we have some interesting family of vertex operator algebra which comes from for this. Now, what is remarkable for me is this conjecture of beam and Rastelli, which says the Higgs branch can be recovered from corresponding VOA as associated variety. This is remarkable because this is vertex operator algebra is purely algebraic object, and Higgs branch is a very interesting geometric invariant. And so in general, Higgs branch is a hypercular cone, but by definition, the associated variety of a vertex operator algebra is only a Poisson variety in general. So the vertex operator algebra coming from 4D theory has a property that the corresponding associated variety should be a hypercular cone. So in particular, symplectic. So this is a very strong condition. And also because everything comes from physics should be nice. But the image VOA obtained as image of a 4D is not Lee's. I explained Lee's VOA is very nice, but this cannot be Lee's in general because this means that Higgs branch is a point. So it's natural to look for some try to relax this Lee's condition for the associated variety to obtain some nice property of a vertex operator algebra, which somehow describe VOAs coming from a 4D theory. And for this reason, we gave the following definition. Vertex operator algebra is called quasi-Lee's if associated variety has finitely many symplectic leaves. So this is certainly some finiteness condition. And the Higgs branch is expected to be quasi-Lee's. And here are some examples of quasi-Lee's vertex operator algebra. This simple affine vertex algebra is quasi-Lie if and only if associated variety is contained in the nilpotent cone. And so the symplectic leaf in this style is just a co-adjoint orbit. And because nilpotent cone has only finitely many co-adjoint orbits, so if a variety is contained in nilpotent cone, it's only finitely many symplectic leaves, and you can also show the converse. So this means admissible affine vertex algebra is quasi-Lie. But the converse is not true. And if you take a so-called Deligne exceptional series, which is a series like this, A1, E2, D2, D4, E4, E6, E7, E8, and consider this special level, you find that the associated variety is a minimal nilpotent orbit closure. So the corresponding affine vertex algebra is quasi-Lie. But for D4, E6, E7, and E8, this level is minus integer, so it cannot be admissible. So this is some example outside the admissible representation. And so with Amaro, we studied this VOA from a different motivation. And it turned out this VOA exactly the VOA appeared in the papers examples of vertex operator algebra coming from 4D theory. Although we have to remove this G2 and F4. Now, what we can say about the quasi-Lie vertex operator algebra. So we can say the following. For quasi-Lie VOA in general, we can say that there is only finite many simple ordinary representation. So ordinary representation means that the character, the trace, so this is well defined. And for ordinary representation, this character converts to holomorphic function half plane. And moreover, this trace function is satisfies a modular linear differential equation. The point here is that the solution space of a modular linear differential equation is by definition an invariant under the natural action of SL2G. So together with beam-rastery conjecture, if you believe the conjecture and the expectation that the X branch has finite many symplectic leaves, this implies the modularity of Schur index of any 4D theory. Okay, so let me explain more examples of quasi-Lie double algebras. So let WKG be the simple quotient of this universal double algebra. Then at least conjecturally, it can be described as an image of simple quotient, simple affine vertex algebra by Dirichlet-Sokolov reduction. So this means we can describe corresponding associated varieties. So if K is admissible, then we get this intersection of the Sroddy slice with nilpotent oblique closure, which is called a nilpotent Sroddy slice. And so this is quite well known if G is ADE and F is a subregular, because it has this intersection has a simple singularity of the same type as G. But you can take any nilpotent oblique closure, and you can take any Sroddy slice. So because simplet leaves here is just an intersection of a coadjoint orbit with a Sroddy slice. So this means is that the WKGF is quasi-Lie for admissible levels. So we have a quite large family of quasi-Lie double algebra. And it's known that this double algebra appear as image for this theory or some Aguilar's double theory if K is so-called a boundary admissible level. So boundary admissible level means that the admissible level is a fractional level. So it can be a shifted level, can be written as so this is a rational number. So boundary admissible means this is smallest as possible. So this must be a check for simply list case. And maybe I skip what I wanted to say here. So there's some implication of this Agras-Douglas theory, but let me skip. And I want to talk about the classes theory. So the classes theory is like, because X stands for so S stands for 6, and classes theory is obtained from the 6-dimensional theory by compactifying on a punctured Riemann surface, as you know very well. So it has a parameter as a punctured Riemann surface, and also a flavor symmetry group, which is a complex semi-simple group. And Moore and Tachikawa gave a mathematical description of the Higgs branch of this 4D theory in terms of 2D TQFT, and up to a conjecture. Now, this conjecture was approved recently by Braverman, Finkelberg, and Nakajima. So you have a nice mathematical description of Higgs branches. And so one of the statement of Moore Tachikawa is that we can, it's sufficient to describe a Higgs branch for genus 0 Riemann surface, because we can glue the genus 0 Higgs branch to obtain Higgs branches for arbitrary genus. So let me explain the Higgs branch for the genus 0 case. So Braverman and Finkelberg and Nakajima constructed the Higgs branches for the R punctured P1, which I write as MTR, as follows. So this is a finite dimensional variety. But to define a finite dimensional variety, you consider infinite dimensional manifold called affine Grassmannian, where G check is a Lagrange dual. And you consider sheaf on the affine Grassmannian, which I denote by AR, which correspond to the regular representation of G check via the geometric Satake. And you consider box tensor product on this product of affine Grassmannian, and you consider a shrink product. And they show that this sheaf on affine Grassmannian is a ring object, so that the corresponding cohomology, equivariant cohomology, has a structure of commutative algebra. So this is a commutative algebra, so you can take spectrum. So you get some algebraic variety, and so the statement is that this MTR is a possibly a singular symplectic variety equipped with a Hamiltonian action of R copy of G check, where so this R is same as R. So this is already a non-trivial statement. And now there are some initial conditions. So MT2 should have two commuting action of G, and so the MT2 is the most simplest manifold which has two commuting action of G, which is cotangent bounded to G, and MT1 is G cross the constant slow slice. The slow slice for the principal nilpotent object. And the most important property is this associativity property. So MTR plus S minus 2 can be obtained by the symplectic reduction. the statement is that the symplectic reduction is well defined, and we get the MTR plus S minus 2. So this is a very fancy way to define finite dimensional so the modularity conjecture was the existence of the symplectic variety satisfying this condition 1, 2, 3. So this means that the MT3 is exactly the Higgs branch of for the genus 0 classes. And
sorry to interrupt. This is the 5-minute notification. Okay.
For type A, so maybe I skip Coulomb. Now we want to describe the corresponding chiral algebra, which is called the chiral algebra of classes. And these people conjecture that the chiral algebra of classes coming from class S, which should be also describes similarly in terms of 2D TQFT. So we should be able to upgrade everything to the chiral algebra setting. So this means we can want to replace G to the corresponding affine Katsumori algebra. And I want to replace a symplectic variety with a vertex operator algebra whose associated variety is symplectic variety X. And that will replace momentum map with a corresponding chiral momentum map. And also we replace symplectic reduction with the relative semi-infinite cohomology, which appeared as a coset construction we study. And this is the right thing to do because we recover the symplectic reduction by taking associated varieties. And there's one constraint that to make sense of this relative semi-infinite cohomology, you have to the level of V1 tensor V2 must be 2 times minus HX. So each level has to be critical. So you have to work on the critical level. And so MT2 is replaced by CDO on G, which has a symplectic associated variety isomorphic to cotangent 1 to the G. And MT1 is replaced by a Drinfeld-Sokolov reduction of the CDO. And the statement is that there exists a unique family of vertex operator algebra satisfying similar properties. So this corresponds to the fact that the modularity variety is symplectic, equipped with the Hamiltonian action with GR. And so Vt is CDO and V1 is and we have also associativity for the VR. And this VOA satisfies the following property that each one is simple and the central charge is expressed as this and have the explicit character formula. And more importantly, we recover the modularity variety by taking associated variety. And this property A and B, these are properties that this chiral algebra of classes should satisfy. So by the uniqueness statement here, this means that we are here must be the chiral algebra of classes. And the last statement that the associated variety of Wira is modularity variety means that the beam-rastery conjecture is true for the classes. So this confirms the beam-rastery conjecture for classes theory. And we can, in principle, compute the chiral algebra of classes, because although it's a heavy computation. And for SL2, MT3 is so I just show you the result. The MT3 is just C2 tensor 3, but MT4 is a singular variety, which is a minimally potent topic closure. And corresponding VOA is a simplified vertex operator algebra. And the fact that this is associated varieties are isomorphic terminal nilpotent topic closure reproves the statement I stated before. And so associativity equation implies this following non-trivial isomorphism between VOAs, and we have nice character formula, which is quite surprising because this is not this character is expressed by non-trivial casuistic polynomial. And for S3, we can also describe that in general, neither of this has a simple description. It's time to stop.
Yeah, we have one.
Yeah, yes. Sorry.
Sorry, are you stopping here? Sorry, are you stopping here?
Sorry?
Are you stopping here?
Sorry, yeah, I'm stopping here. I'm sorry about it.
No, it's okay. Thanks so much, Tomoyuki, for this nice talk. Now I'm going to unmute everyone, and please accept that and give a big hand to our speaker. Now we're going to take questions. If you can either raise your Yes, are there questions? Please use the raise hand option. Yeah, so there's a question from, yes, okay, I see there's a question from Edward Witten, so I'm going to unmute. Yes, okay, Edward, you can.
Okay, well, actually, I have a question that should have been right at the beginning, as you'll see. You said that for an integrable affine Lie algebra, the associated variety is trivial. So that should mean, but it's obtained by taking the quotient of the whole vertex algebra by what you called C2. So the current generator should be in C2, which seems to say that C2 is a descendant. Sorry, that the generators are descendants. So I was puzzled. Obviously, I misunderstood that. So I can't tell if people heard my comments.
Yeah, I can hear you.
I think
you have Tomoyuki, you have to unmute. Yeah, you're muted.
Sorry. Yeah. So the associated variety is a trivial as a reduced scheme, but as a scheme, it's not trivial. So it's a fact point.
Okay, fine. All right. So what the statement means is that a sufficiently high power.
Yes, it's yeah.
Okay, thank you.
There is another question from David Agato. So the question is, how does the associated variety behave under VOA extension?
If the extension is finite, we expect that the associated variety is rationally equivalent. But if it's an infinite extension, we don't know. We don't know how to control. Does this answer?
David, does this answer your question? Okay, he's happy. He said thank you. Are there any further questions?
There's a question from Cameron Buffer.
Yes. Cameron, you can ask the question now.
Yes, very nice talk. I have a question. How much does this perspective from the vertex operator algebra help us perhaps in classifying the n equal to 2 theories or subclassifying them depending on some conditions? Is there a way to get insight into the totality of them in some form?
So if you believe this map is injective, this means that if you are able to classify the image, you should be able to classify the n equals to 2.
Let's assume it's injective, but is there a way? I mean, this is probably a vast class. Is there a way like you classify it according to some subclassification in terms of some complexity or something? Is there some kind of program there?
No, unfortunately, it's a big open question.
Okay, thank you.
Thank you. Are there any other questions? Yeah, Edward Witten has another question. I unmuted it.
Yeah, as well as Higgs and Coulomb branches, there are mixed Higgs-Coulomb branches in general for n equals 2 theories. I assume what you've been calling the Higgs branch is the case where the Coulomb branch is trivial. But I wonder if mixed branches mean anything.
Sorry, I cannot answer that.
Okay.
Maybe someone else can answer for me.
I guess we can move on to the next question. I do not see any other question. So if there are no further questions, let's thank the speaker once again, and would move on to the next. We have about 10 minutes, so we'll take a short break, and we'll be back at 3 p.m. local time. Thank you.
Thank you for listening.
Hi, Jörg.
Hi.
I have made you co-host, so you
Okay.
can just check
Oh,
if
yeah.
your screen sharing works.
Right, let us try. So I try the one.
Right.
Let me see something. Okay, let me see. Let's see. Does it work on your side? I don't quite see myself here. Let me stop it and try something else. Let's try to share my desktop and make it full screen then. So it says I am screen sharing, but it seems
So,
you
So
cannot.
when you screen share, does it ask you to bring something to the front? Because I usually get a bunch of different windows that are windows that are open, and then I have to select the one that has my talk in it.
Yeah, okay. I mean, I tried two things. One was to try the one with the PDF or just the desktop. So this window I got, and then I just clicked share. Maybe let me just redo it one more time.
Okay.
Good. So now I have this screen where there's desktop preview and so on. And now all I can do, it seems, unless I do something advanced, is to click share, but this didn't quite work. So let me try one more time.
So if you go to, if you click on that, and then if you go to the presentation.
So, okay.
So you're viewing with preview, right?
That's right, yeah.
If you open your file and you click on the top of the screen, you should see something that allows you to view the PDF in presentation mode or full screen.
Yeah.
Presentation mode or to work, I think.
Good. So I do click. So I click the share.
now it's working, I think.
And now I try to enter full screen. Can you see
There
it
you go.
now?
Perfect.
Yep.
Yeah.
Now it looks good?
Yep.
Okay, this was the missing bit. Good. Was just to go to the full screen. Okay, so then basically I'm all set.
Okay, so we'll
And
start up again in 7 minutes.
very good. Thanks for.
I'm going to give you a 5-minute notification.
Good.
Hi, everyone. Welcome back. Very quickly, so we're going to take the questions at the end of the talk. So I'm now handing over to our next speaker, Jörg Teschner, and he's going to talk about the geometric characterization of topological string partition functions.
Yeah, thanks very much for the introduction, and thanks to the organizers for setting up the conference in such a nice way under unusual and in some respects probably difficult conditions. What I want to talk about is joint work with Joanna Koman, Pietro Longhi, and Eli Pomuni. And yeah, so let me jump right into the problem. So here, yeah, I'm trying to formulate the problem we have been trying to address, which is to get a, well, ideally geometric and analytic characterization of topological string partition functions. So what we will consider is A or B model topological strings on Calabi-Yau manifolds. Say when we talk about A model, we would call them X, otherwise Y. And good, in the B model, the worldsheet definition would yield a priori formal series like here, where we sum over genera. So there are contributions of all genera to the topological string amplitude or topological string partition function. And well, in general, it is not clear if this can be actually summed to represent an actual function or anything alike. So this is the question, do there exist functions having this series here as asymptotic expansion? And of course, this comes with obvious questions, namely, if so, which space are these functions defined on? And secondly, well, do we really want a function or maybe a section of a line bundle or something even more general? In any case, yeah, even a semi-optimistic scenario would be that the z-tops, which are defined by a summation of a sort of the series, could be locally defined functions on, well, depending on whether we talk about A or B model, either the Kähler moduli space or the complex structure moduli space of the Calabi-Yau in question. So if, for example, we're talking about the Kähler moduli space, then we would be considering this as a locally defined function of, say, a collection of coordinates on the Kähler moduli space. So this would yield a concrete representation of this object. And yeah, so somehow the main theme of this talk is going to be whether there may exist natural geometric structures on, well, we will mostly focus on the complex structure moduli space, but of course, the other guy is related by mirror symmetry, allowing us to represent the top as a local section of a sort. And for a class of local Calabi-Yau manifolds, we shall offer, that is, propose such a description. And I will, towards the end, hopefully discuss a few hints that such a discussion could even generalize beyond the class that we consider here, which is defined as follows. So we consider local Calabi-Yaus defined by equations of this form. So we have here 4 complex variables related by one equation, uv minus some function f sigma of x and y equals to 0, which is such that well, the 2-dimensional curve, that is one complex dimensional curve defined by just setting this function f sigma of x and y to 0, is, well, a subset of the cotangent bundle of some Riemann surface, so which we assume to be given once and for all. And we have in addition a quadratic differential on that Riemann surface. And so this here would be a curve in the cotangent bundle of that Riemann surface defined by a quadratic differential, which then in turn defines a local Calabi-Yau by this equation. So this is some, well, reasonably interesting and large class of local Calabi-Yaus, which have appeared in the context of geometric engineering of the so-called class S theories that we just have heard about in Tomoyuki's talk. Now, what is the complex structure moduli space? Well, that's pretty obvious by the description I just gave of these local Calabi-Yaus. It is the space of pairs C, the Riemann surface, that is the complex structure, of course, matters, and Q, the choice of a quadratic differential on that Riemann surface. That is the concrete representation of the moduli space of complex structures in the case of our interest. This immediately comes with some important geometric structures, which, well, come almost for free by this very description I gave. Namely, quite important is in particular the special geometry, which is familiar from Seiweg-Witten theory, where we can take the periods of the square root of the quadratic differential, which would be called the Seiweg-Witten differential, as coordinates, and there is a relation between these coordinates allowing us to introduce the prepotential as the potential, giving us here the, say, conjugate or dual set of periods when we start here with the periods over a basis for the first homology of this curve sigma. A canonical basis which has here, well, a polarization built in. Well, secondly, what's going to be important is that this setup basically comes with an integrable structure for free, as was pointed out by Donaghy and Witten, and then encoded in a rather general theorem by Dan Fried, namely associated to the geometric structure called special geometry. There is canonically a integrable structure. Basically, we can, over each point of the base manifold, which here is identified with moduli of complex structures, define a torus by basically this equation, where here the main data parameterizing the type, well, the geometric structure of the torus is the period matrix tau, which in turn is the matrix of second derivatives of the prepotential. So this is then defining a torus fibration, so we can project this moduli space M int, well, where int can stand for integrable or for something else, which I will mention in a moment. We can project it down to the bases, which are the moduli of complex structures. Yeah, so this is equipping it with what we can call an integrable structure. 3 other pictures or incarnations of this moduli space will be of some importance. Well, here we have these tori. I mean, we can identify these tori with the Jacobian or prim varieties of this curve sigma. And via able Jacobi maps, that is some classical algebraic geometry, of course, there's a one-to-one correspondence between points on these torus fibers and the divisors on sigma. So I can identify this moduli space with a moduli space of pairs, where we have on the one hand the curve sigma, and on the other hand the divisor d, associated to these points, well, b here by able Jacobi. And it is this type of geometric object is rather familiar from a theory of the Higgs pairs initiated by Nigel Hitchin. So there's an isomorphism via a famous construction of Nigel Hitchin's of, well, the moduli space of Higgs pairs, holomorphic bundle, and Higgs field phi to this moduli space of pairs sigma and a line bundle on it, or equivalently a divisor on it. I'm here, of course, skipping some details, which in general will be relevant. And say for the embedding in the, say, Calabi-Yau context, it's also important to remark Diaconescu, Donaghy, and Pantev have identified this moduli space in question with the intermediate Jacobian fibration, which, well, one can define quite generally in the context of Calabi-Yau manifolds. And yes, what was shown is that if you specialize it to the class of local Calabi-Yaus we're considering here, it would reproduce the Hitchin's description of the moduli space of Higgs pairs. Okay, so that's the playground we want to work with. This is the class of examples for which sort of we have a reasonably concrete story, a reasonably concrete prediction or proposal to make. Okay, so this slide is to summarize basically our approach or our starting point before we summarize sort of the main outcome of our investigations. So basically what we started from, and which then basically also yields confirmation of the proposal we're about to make, are the observation that some of these local Calabi-Yaus can be represented via limits that are familiar from the geometric engineering of gauge theories and string theory as limits of toric Calabi-Yau. And when this is the case, then we can compute the z-top with the help of the topological vertex. Of course, we need to take the limit. This needs a little bit of care, but in any case, it can be done for a subset of the y sigma. I don't know if it can be done for all of the y sigma, because, for example, in higher genus cases, I wouldn't know how to do the geometric engineering of this class. But anyway, we have a few examples where we can do that, and there we can compute and compare. Well, then it's a reasonably old and famous story that what you compute with the topological vertex can be compared to results of the instanton counting as developed by Moore, Nekrasov-Shatashvili, Losev, Nekrasov-Shatashvili, and Nekrasov. And then combined with the AGT correspondence, one finds that, well, the concrete computations with the help of topological vertex, what they actually produce are conformal blocks of the Virasoro VOA at c equals to 1. That we have a rather special central charge is, well, due to the fact that in this context, we're not going to talk about refinement. So we have, and this is appropriate for really having this geometric picture of the topological string, etc. So this is the case we are. And then there is also a reasonably old and famous story relating the z-top in this case to a counting function of d0, d2, d6 branes. And then furthermore, by appealing to further string dualities, the prediction was made by Dijkgraaf, Holland, Sulkowski, and Waffa that you can arrange by doing this somewhat funny transformation, which will play a very important role throughout the whole talk. You can sort of basically take a transform of the z-top, the object we're interested in, where you, well, this is if you here just redefine variables to have an I. It's like a Fourier series, but with very special Fourier coefficients. So this object, on the one hand, should then also be related to a counting function where you also are counting the d4s, which is related here to the P. And then the main prediction based on string dualities of Dijkgraaf et al. Was that these objects should have a representation as a free fermion partition function, basically on that curve sigma that we started from, that basically was defining our local Calabi-Yaus. So this would be nice in reducing really the computation that we want to do to the computation of free fermion partition functions. And this of course could bring into the game all the nice relations between free fermion partition functions, tau functions, integrability, and so on and so forth. And some modern variant of this plays indeed an important role in our story. Let me stress that, in general, you can invert this relation. So you should be able then to recover the z-top by inverting this relation from the free fermion partition function. And that is sort of the attitude we're taking here. And then what we used was recent progress on the relations between free fermion conformal field theory, tau functions, and Virasoro VOA, which was stimulated in the paper by Gamayun, Yorgov, and Lisovy. And the version, this was proposing a conjecture, basically relating giving a new description of the isomonodromic tau functions in terms of Virasoro conformal blocks. And this conjecture was then proved in joint work with Yorgov and Lisovy. And this gave some interesting interpretation of this series in particular, which I shall return to perhaps a little bit towards the very end. But in any case, this is sort of the background. These are the tools we were using. And then, we were trying to interpret the results of all that in geometric terms. And this led us to the picture I want to formulate now. So here is the proposal in a nutshell. So really now I want to sort of throw a little bit away the ladder we climbed up on and formulate in as geometric terms as possible what the resulting picture is. Down here, you're seeing again this formula relating the top, the object we are ultimately after, to a tau function. So this really is a kind of refinement of the formula we just looked at here on the previous slide, relating the z top to free fermion partition function, where of course you should think of now here the left-hand side being the free fermion partition function. Good. In any case, so what geometrically are our main players? It is on the one hand the moduli space of complex structures on the Calabi-Yau in question, and then the torus fibration that, thanks to special geometry, is canonically associated to the special geometry of these moduli space of complex structure. So that would be the intermediate Jacobian fibration. The claims are, there exists on the one hand a canonical one parameter, and the parameter h bar here is identified with the topological string coupling constant. A canonical one parameter family of deformation of the complex structures, which will be defined by producing an atlas of Darboux coordinates on something which is reminiscent of twistor space. And ultimately, I believe it is related to some twistor space. Maybe I have some comments towards the end. But in here, it is just introduced as the product of M int tensor times the product, the Cartesian product with C star. And secondly, and here come the main players, namely a line bundle with a connection. And the main point is the way how we describe basically how this object here, the tau function, changes from chart to chart. The claim is going to be, and I will detail this, that the transition functions are basically canonically defined by the changes of coordinates from one patch to the other. So therefore, the very data defining this atlas, thereby defining the deformed complex structure, canonically also define these transition functions, defining the line bundle as a variant of the generating functions, which we call difference generating functions. This is just because, the usual derivatives in generating functions from symplectic geometry will be replaced by taking finite differences. I will explain how. So these are then what represents the transition functions defining the line bundle, and then say the flat sections of the connection, well, these are our tau functions. And good. So this is basically what defines the left-hand side. And then the claim is that for all of these charts, we do have such a Fourier series expansion defining here the z top we're after as the Fourier coefficients on the right-hand side. So this is the claim in a nutshell. And of course, I owe you more explanations about the ingredients here, which I want to do in the next few slides. Okay, so first of all, there is the story of how to define a, say, well, H-bar deformation of the complex structures we're starting from. And this is going to be a game that has appeared in a priori different looking context, which is the work of Gallotto, Moore, and Neitzke, and well, the variant of that that we're using here and discussing here is what appeared in more recent work of Tom Bridgeland. Well, for those who know about this, it is basically what is called the conformal or massless limit of the story of Gallotto, Moore, and Neitzke that is of relevance here. So we want to define the H-bar deformed complex structures by an atlas of coordinates. On the space here, we have been talking about a collection of charts. And in these charts, we have Darboux coordinates. And well, these define the complex structure in the usual sense, namely for each value of H-bar, then we declare these here to be, well, holomorphic functions with respect to the such defined complex structure. You may note I have a little more than one maybe usually has, namely there is a polarization built in, which is kind of important because the polarization is going to used here basically in this formula where we have, well, the x check coordinates here and the x coordinates here. So, I mean, we need a polarization to write down such a formula. Good, then the important thing is basically, or the most important thing is, of course, to describe the changes of coordinates from patch to patch. And the point is, this is, or the claim is, this is going to be given by also quite familiar formulae from the work of Gallotto, Moore, and Neitzke, namely, this is represented by cluster-like coordinate transformation. So we have a rather simple rational form when we take exponential functions of these coordinates little xi. There's a little bit here of notation. So we have a charge vector here also split according to some polarization, which we with some symplectic form contract into the coordinates xi, which again are arranged into such a vector. But yeah, it's basically defined by explicitly writing out the result as notation that is handy in order to write the changes of coordinates into a compact form. And the crucial data here are some rational invariants, which are piecewise constant then over the moduli space here we're talking about. So these are these rational numbers omega of gamma, which are subject to the so-called Kontsevich-Solomon wall crossing formula. So there are some constraints which basically, you could be seen as constraints for the very possibility to define a consistent, say, deformed complex structure in this way. This appeared as smoothness condition in the case of hyperkähler metrics in the work of Gallotto, Moore, and Neitzke. Here we're talking just about the complex structures. Last but not least, and of course I have to be somewhat sketchy and schematic here in view of time, but yeah, what is relating the new coordinates to basically the old coordinates for the base manifold, which were here defined as these periods. We have had these special coordinates for the space of complex structures, that is the base of the torus vibration before. And so now the requirement is that when we send h bar to 0, then as the leading term, we recover those. And quite interestingly, and I don't have the time to go into much details about this, then as sort of the next to leading bit, we find coordinates for the torus fibers. Here is the more precise relation. There's a little bit of redundancy, which however turns out to be inessential in some precise way. So anyway, this is the asymptotic behavior where then the actual coordinates for torus fibers are some combination where again tau is the period matrix defining these, well, the complex structure of the torus fibers. Okay, so this is, if you want, defining, and there is more sophisticated formulations of this, but the problem to find, given the data omega satisfying conceivable wall crossing formula, then these coordinates, this can be called a variant of the Riemann-Hilbert problem, and that is the point of view, well, going back to Gayotto-Muranidze and more recently further developed by Tom Bridgeland. There are two known ways to solve this problem. On the one hand, the work of Gayotto-Muranidze gave a solution by, in terms of nonlinear integral equations. So whenever you can solve these nonlinear integral equations, which you can often do by iteration, and there are in some cases results concerning existence and uniqueness of these NLIE, well, then they basically produce from the given input data, which are here our coordinates A and theta, then the desired coordinates x sub gamma of h bar, which represent the solution to the, well, BPS Riemann-Hilbert problem. That's how I sort of want to call it for having handy terminology. There's a little trouble here in this case with the NLIEs. I think for the case at hand, which is this conformal limit, the convergence typically of those is relatively slow, and I am not sure if, say, the results on existence and so on would hold in this case. Typically, I think it requires these, well, what is called massive deformation. So therefore, well, but I think, yes, ultimately for the theory, it is important that there should be this other way of representing the solution. Anyway, there's a lot of like mathematical problems that sort of, I mean, I do not claim that here, especially in this part, everything is already rigorous mathematics at this time of, what I want to focus on is the second way of solving it, which uses something which is called quantum curves, and I will elaborate on what this is. And well, for the moment, let's just think of differential operators of this form, which basically are built from a deformation of this quadratic differential, which was defining our curve sigma in the first place. I will, what kind of deformation I will mention in a moment. And then the basic idea here is that the coordinates we're after, the solutions to this BPS Riemann-Hilbert problem, would be defined by employing the Borel summation of exact WKB solutions of the differential equation that you can, well, define from this differential operator, that is whatever is annihilated by this differential operator. This is then what allows us to define these coordinates. So this is the basic idea, but we're going to talk about this a little more in, well, the next few minutes. So the basic idea here behind is, well, we were basically defining our curve sigma by some equation of the form y squared is q of x. And well, there is a canonical symplectic structure here where y is the conjugate of the variable x, which is a local coordinate on the curve sigma. What this very much suggests is to do the canonical quantization in order to introduce the h bar, which is then just in schematic form amounting to the replacement y by h bar over I d by dx. So then from this equation, what we get is exactly this differential operator that we already saw on the previous slide. And well, what this is basically describing is a class of holomorphic connections called operas. So there is a whole well, theory about generalizations of this type of differential operators, which, well, is not so important for what I'm saying today. What is important is that there is an essentially canonical generalization which basically deforms, h bar deforms these pairs sigma d, which then was representing, according to the previous discussion, this torus vibration. This comes by allowing apparent singularities. These are singularities which in PSL2C have trivial monodromy. And you see, these have a very peculiar form with here the leading term in the Laurent expansion having a 3/4. And then if we're careful here about powers of h bar, it is down by a power of h bar squared. So if we just formally turn off h bar, so send h bar to 0, all these apparent singularities would disappear. So this basically is natural and is related to this fact that also here these coordinates on the torus fibers came basically at the next to leading order of h bar. So basically also here the dependence on the new variables, which are the positions of the apparent singularities, basically comes in higher orders in the h bar expansion. There's a relation between this, but I don't have the time to go into much details here. I have discussed this elsewhere, or you find the discussion in the papers. So this is what we want to study, operas with apparent singularities. That is, the QH bar has apparent singularities of this type. All right, so the conjecture then is that the solution of this, what we call BPS Riemann-Hilbert problem, is given by the composition of the holonomy map with particularly nice, that is, rational coordinates for the space of monodromy data, which is what is called the character variety. That is the algebraic variety having as the coordinate ring the trace functions, traces of holonomies or monodromies of this differential operator. And we want very special such coordinates. So first of all, we want coordinates which give us the trace functions, as rational expressions of the coordinates. And secondly, we want them to have a Borel summable h-bar expansion. And basically, the idea, the main claim is this is, basically uniquely determines coordinates. So this determines very distinguished coordinates, and these very distinguished coordinates are these very distinguished solutions to the BPS Riemann-Hilbert problem we're after. So we're not having here any freedom of coordinate choice. In the end, we want a canonical coordinate choice determined just by the data that we put in. All right, so something about exact WKB. So what are the essentials we need to know about that? So we're talking about the solutions of the differential equation defined by the quantum curve. That is this differential equation here on the top right. Good. It is, of course, well known how to expand the solutions into powers of h bar. This gives us series of this form. So we can write it as an exponential of some integral, and the integral is a function that is determined from the Q by something called the Riccati equation. So the S is the solution to the Riccati equation. You can solve this equation easily as a formal series in h bar. The leading term is going to be here our square root of Q0. And this gives us a formal series. We're then taking, we're having here in the leading term a choice of sign, and we're going to take an odd combination of the solutions determined by either choice of the sign in order to define here this, this function S we're integrating over. So this gives us a standard way to construct in a series expansion in powers of h bar the solutions here to this differential equation. Now, there are some results. Unfortunately, the status of these results is a little, unclear. But, I think there is little doubt that these results are ultimately correct, which would say that this series here is in fact Borel summable. That is, it canonically defines an analytic function of our h bar away from Stokes lines. What are the Stokes lines? The Stokes lines are defined by the equation that the imaginary part of sort of a canonical coordinate that you can define here from the square root of Q by just taking this, the primitive thereof, and here we're taking with, we're modifying the phase of that, that this imaginary part of this coordinate is constant. So this defines lines on our Riemann surface, and so this decomposes the Riemann surface into regions. And within these regions, so if we stay away from these lines, then we have Borel summability, that is canonically defined solutions chi of that form. And the guys we're after, which are sort of in this way canonically defined by what we put in, are called Vorosh symbols. So under these conditions, the type of conditions I mentioned, they can be Borel summable. And if they are Borel summable, then they can represent the ingredients to the solution of the BPS Riemann-Hilbert problem we are after. So there are proofs attributed by many papers to unpublished work of Koike-Schäfke here of Boros homability, and Nikolaev, I understand, is preparing an independent proof, hopefully to appear soon. Okay, so, well, the Boros summability, by what I just said, depends on the topology of the Stokes graph formed out of the Stokes lines, where you basically plot these Stokes lines here, the solutions of these conditions, which start at branch points of this covering defined by the quadratic differential Q. Two extreme, in a sense, cases are of interest. You can, on the one hand, have the case, which is kind of the most generic case, where the Stokes graph defines a triangulation of C. What is here on the right in the pictures are some Stokes graph for 3 punctured spheres. Well, maybe I should enhance it. The punctures are these little blue dots here, here and there. So there are 2 punctures and one is at infinity. And when you then just connect the punctures in such a way that you stay in a Stokes region, then you will get a triangulation of the Riemann surface C. Graph and triangulations of the surface C. For special choice of the quadratic differentials, you can have another type of Stokes graph, which has basically only, well, saddle connections, that is Stokes lines starting and ending at the branch points, yeah, for its definition. And what they define, if you have, well, a more general situation with a Riemann surface, they define a pan-stick composition of that Riemann surface. So you have these two, I mean, as the two cases of triangulations and pan-stick compositions, they are associated to corresponding types of coordinates. So Boros symbols would then always correspond to coordinates. In one case, they're known to correspond to the Fock-Wontroff coordinates. That's the case. That's what is associated to triangulations of C. And in the other case, as was also pointed out in work of Hollens and Knightsky, in the other case, we have Fenchel-Nielsen type coordinates. That is, coordinates which restrict, when we go to a real size, to the Fenchel-Nielsen coordinates from Teichmüller theory. So there is a nice situation, and well, much of, say, there's a lot of mathematical work already on the cases where we have triangulations as Stokes graph. In particular, Dylan Allegretti has proven the conjecture of Tom Bridgeland's that for that case, the Boros symbols are Fock-Wontroff type coordinates solving the BPS Riemann-Hilbert problem. But for us, it turns out, and that was sort of causing us considerable headaches, that what we need really is the extension of all that to these other cases, where we have Fenchel-Nielsen type networks and Fenchel-Nielsen type coordinates, which are associated to pan-stick composition. That is interesting in particular. I mean, well, the corresponding quadratic differentials, they're also called Jenkins-Tribble differentials. And these are what we need in order to really extract, say, the topological string partition functions, which we can compare to topological vertex computation. So this case is of particular interest.
Sorry to interrupt you, 5 minutes.
Thank you, yes. Okay, so, well, let me therefore turn to the second half of our proposal, which is that there's a canonical pair of a line bundle and a connection where sort of, yeah, which is basically defined by its flat sections being the tau functions, and the tau functions are the objects from which we want to extract the partition functions by these Fourier series. So the point is, if these guys here are then meant to be local sections of that line bundle, which we are about to define, then they need to be, then the change from patch to patch must be of this form. That is, there are some functions which are defined here by, of the coordinates xi, xj, which then multiply, well, a section in one patch, yielding the section in the other patch. The point is to describe what are these functions here. And the claim is they're very special ones. They're difference generating functions, namely basically defined by the changes of coordinates that were defining the H-bar deformed complex structure. So I have to speed up a little bit, perhaps. So what's the point? The point is really the very possibility to do such Fourier series representations. Well, this is equivalent to these tau functions satisfying difference equations. So there's obvious periodicity with respect to check variables, and there is a kind of difference equation. If we shift the unchecked variables, they spit out the exponential of the checked variables. So this is, if you wish, deformed special geometry. Now, the coordinates which we consider here are such that this change of variables can be solved to get the check in terms of unchecked variables. And then, yeah, the change of variables on the level of the tau function is given by some function Fij, which, in order to ensure that in the both charts I and j, we have these properties, that is the possibility of this expansion, or equivalently these difference equations satisfied, well, we need shift relations for these transition functions of this form. So if we shift xi, it spits out the exponential of the conjugate to xi, and if we shift xj, it spits out the exponential of the conjugate to xj. So this is, well, there's the obvious relation or similarity to generating functions, except we have replaced taking derivatives by taking finite differences. Here's a basic example that I shall skip for reasons of time. So it is just worked out how to compute such a thing in basically the basic case of a flip, to which in the end of the day, everything reduces. We find something expressible in terms of the Barnes G function, or it turns out you can also express it in terms of Rogers-Stein logarithms. Okay, so I have to come to some conclusion, but yes, maybe I shall more or less manage. So here is the summary then of what we did for these class sigma cases in the recent paper that is on the archive, that appeared on the archive in April. So there is some work in progress which works out. I mean, there we basically work it out in some basic examples like 4-punctured sphere, and well, in some work in progress, we will generalize to other cases. So this is to explain how to define the solutions of the secondary Riemann-Hilbert problem by basically combining free fermion conformal field theory methods with the exact WKB used basically in the way I explained. So let me stress some features of the output of that. So first, well, I stressed the importance of going beyond just the case of triangulations, namely to include the cases which have Jenkins-Tribbles differentials and which define a pan-stick composition. And the proposal covers those. What is important, and that is technically the hard part, is then we need to also describe the change of coordinates between Fock-Goncharov, Fenchel-Nielsen, and so to go back and forth. So we need to enlarge the picture into this. Turns out Fenchel-Nielsen is really a close relative of Fock-Goncharov. In some sense, you can see it as a limit by the juggle of Galliotomur-Neitzke of those. Anyway, wherever available, that is on these real slides represented by Jenkins-Tribble, we can compare in some cases with topological vertex computations and find perfect match. And secondly, important work of Itz, Lissovy, and Tukey for the 2-punctured sphere case with irregular singularities has pointed out there is a strong coupling expansion of the tau function. And well, our proposal covers this. This in particular serves as motivation to, from the other point of view, to extend to Fock-Goncharov type coordinates. So the point is that in our proposal, the exact WKB for quantum curves fixes the normalization ambiguities, and therefore the H-bar deformation in this scheme is as canonical as possible. Good. So here is the concluding slide. There are some more like takeout slides that you could ask for if you want. So there's a bit more you could look at in discussion. But anyway, I want to conclude by saying that the high genus corrections in the topological string theory on X are encoded in a canonical H-bar deformation of the moduli space of complex structures on the mirror Y of X. And there are some hints that this picture may generalize beyond the class sigma examples. And I want to stress in particular, and maybe if I'm given one more minute, I can say a few more words about that. there is a very intriguing relation to the work of Alexandrov, Persson, and Piolin on the geometry of hypermultiplet moduli spaces. And furthermore, the relations I mentioned already to the program of Tom Bridgeland he is currently running. And there are some, and this is embarrassingly the part I understand the least, hints that also it is related to the proposals of Marcos Marinho and collaborators, what we are doing here, but this is somewhat, annoyingly quite unclear to me at the moment. Anyway, very quickly, let me say something on the relation to Alexandrov, Persson, and Piolin. What they have proposed is they have proposed a geometric scheme for NS5 brane corrections to the geometry of hypermultiplet moduli spaces. And the point is they have come up with something which is very similar, and I believe essentially, at least in the example we're looking at, identical or equivalent to what we're proposing here. So they have proposed to describe quantum corrections using twistor space geometry by Dabou coordinates. And then by combining mirror symmetry, S-duality, and twistor space geometry, they proposed that the correction for one NS5 brane is encoded in locally defined holomorphic functions H and S5 of coordinates xi check. So there's also some Dabou coordinates, polarization, and so on, having an expansion of this form. And of course, well, this looks familiar. This looks like exactly what we have seen and what was playing key role in our approach. And then furthermore, they observed that using the Donaldson-Thomas Gromov-Witten relation of MNOP, the coefficients here, in fact, should be identified, at least for this class where it's applicable, with topological string partition functions. So this suggests that, well, on the one hand, I mean, I think this, hasn't been pushed, it hasn't been applied very much yet because there were some open questions about this proposal. I think at the very least, our results can be taken as a confirmation of this proposal in an interesting class of examples. And from our point of view, I would take then the relation to this APP framework as a hint that there's a good chance that this picture generalizes beyond the class of examples we've studied. And maybe here I shall stop and thank for your attention.
Thank you, Georg. Thanks so much for this beautiful talk. Now I'm going to unmute everyone, and then please give a big hand to the speaker. Okay, so we're going to take questions now. Please use the raise hand option. Edward Witten has a question. I have sent you the unmute.
I'm afraid this is a question that should have been better at the beginning of the talk. I don't understand the framework in which what makes one hope to put the topological string partition function in this framework. What is it that points us toward this generalization of this twistor-like construction, for example? I know it's a ridiculous question, I'm sorry. You're muted, I'm afraid.
Sorry, you're muted? Yeah.
Okay, now, well, concerning the framework, as I tried to explain on one of the first slides, the type, I mean, the way we arrived at this proposal was indirect and winding, in the sense we really tried to bootstrap ourselves up from cases where we know the result, which then we were trying to interpret geometrically. So there were, it was based on the cases. I mean, we were starting from the cases, and that was the first paper where for associated to 4-punctured sphere, that is NF equals 4 theory, where we can compute in some channel with a topological vertex. Good, there is we observed there are flop transitions, which would then modify the result by some factors. And we were starting to ask ourselves, what is the deeper meaning? What is sort of a geometric picture behind? There ought to be, and that is of course something that topological vertex cannot easily provide, also a representation of the S-duality of the NF equals 4 theory, which corresponds in terms of conformal blocks to the usual channel duality between S and T channel. Furthermore, then we looked at other examples like the pure the pure SU2 theory, where also topological vertex computations are available. But there again, what you get from the topological vertex would not cover the whole moduli space of complex structures. There is the so-called strong coupling region. And then using the relations to the free fermions and the tau functions and the result of Itzlusovic-Tücki I mentioned, well, it was observed that, yeah, on the one hand, what seems to be the case, or what, I mean, it was sort of phenomenological observation. So in the cases associated to weak coupling, we could attribute, I mean, the coordinates related to this would always be of the Fenchel-Nielsen type, but in the strong coupling region, the coordinates which play the same role in the sense of appearing in these Fourier series expansions, interestingly turned out to be of Fock-Gontroff type. And okay, so these were sort of the starting points, and thinking further in this class of examples about a geometric picture which would naturally encompass all these cases and combine them into one natural geometric object, one natural geometric structure, led us to the proposal I was presenting here.
Sorry, you're muted. Edward, you are muted. Okay, so we have two more questions. One is from Mina Aganasic.
Hi, Jörg. I'm afraid my question is very elementary. Why would you? Could one do this for the original geometry of the topological vertex? In other words, not take some 4-dimensional limit, but stay within the original framework. Even there, it seems that you're giving a new reformulation of the theory. So,
I believe so. Yes. Of course, somehow the interest here arises. I mean, sort of this becomes interesting only when you have, say, some webs or some glued vertices which are interesting enough, which have loops and so on, such that you have all these moduli and so on, which play the crucial role in this proposal, right? But on the other hand, I think it's sort of the canonical next step to take is to do this, say, for Toric Calabi-Yau, some interesting class of Toric Calabi-Yau. And I would think that, I mean, there are some partial results by Jimbo and collaborators, and a recent paper by, I mean, anyway, there appears to be simply a Q deformation of these tau functions, which would then be the basis for doing a similar story as we did in the Toric case. And I think, yes, it would be very natural and very nice to do that as one of the next steps.
So in these Toric cases, in a paper with Digraph, Marino, Clem, and Vafa, we did have the paper that, not the topological vertex paper, but the one after. Mm-hmm. we did have a way of sort of quantizing these quantum curves, except what it did not give, it would give basically open string amplitudes only, mm-hmm. and never just the purely closed string ones. So firstly, it will be obviously very nice to have this, but it seems that this, if there's a natural setting for your story, it should be that, not these theories where you have to take limits and so forth.
Can you still see my slides? This is sort of the last of the takeouts.
Oh, okay.
Which basically addresses exactly this. So, which also has a nice relation. Can you see the slides, or shall I?
Yes.
Okay. Okay, so well, maybe I can make it even a little bigger. Good. So indeed, you can go from the purely closed string situation to an open closed background by inserting the branes that you invented or that you found. And yes, I think this is sort of really very nicely playing with this picture, and especially this free fermion representation. And I think here is sort of the natural starting point for clarifying the relations. So what I think I can say is, well, first, we do have already a generalization. Okay, here we stay maybe in these class sigma, that is geometric engineering examples, but I think here really, yeah, you have the starting point to go up and go 5-dimensional or go toric. Well, the point is that simply there is a generalization of this formula on the level of the tau function, where you then consider free fermion expectation values. So they have a similar representation where what appears then here, what replaces the thing here on the right-hand side would be expectation values of degenerate fields of Virasoro algebra. And I believe these are the guys, I mean, really these fermions in your paper with Dijkgraaf and Albrecht and so on, these fermions are these degenerate fields, really. I think it's clear when you also, I don't know, there was more recent work, for example, by Sergei Gukov and collaborators relating this to the geometric engineering of the surface operators and so on. I mean, this is the story I'm talking about. And yeah, so there's again, you see, there's again these two dual pictures, right? The really B-model picture is here. This is quantum, you have wave functions and so on. And it is this magic transformation which basically brings you to the dual picture here of Dijkgraaf, Holland, Sulkowski, and Waffa, which then makes it all classical and really introduces free fermions proper. So here in particular, the psi would be then the solution to the Riemann-Hilbert problem, which plays sort of the crucial role, which in turn then, in our case, would be determined by exact WKB and so on from the quantum curve. So yeah, and this is sort of the other part of the coin here. I would then, so you have here basically as this basic object, this solution to the classical Riemann-Hilbert problem that you have in this context. And well, this is of course what then basically is created by introducing the surface operators or their geometric engineering by your brains. And then in this way, you're making visible the fermions, the open string sector makes these visible and so on. But again, I think it's very important conceptually then to notice this transformation, which is really the transformation between sort of the quantum world in which these fermions are getting quantum, so they have this wave function story and so on, and the classical world where really we have then a classical solution to the Riemann-Hilbert problem on the left-hand side. Okay, well, I don't know if this was useful.
Well, okay, so anyway, this sounds wonderful, and it will be really great to work this out. And these what you call the 5-dimensional cases, I think are even more natural than this setting. In particular, you don't have to take any limit, and they're also related to conformal field theory, right? Well, not to deformations of conformal field theory. So,
okay. Sure.
Okay, thank you.
Okay, we have basically. I think we have time for one more question. So I think next is Arnav.
Okay. I have two questions actually. So yeah, we'll see how that goes. One is shared by Andy Neisky, so he can follow up if I'm not clear enough. These locally defined holomorphic functions T of x and x hat that he frequently referred to, are they actually globally defined holomorphic functions just defined in terms of local coordinates that are changing, or sections of lines, or what are they?
Okay, they could well have an analytic continuation to all of this space, but that is not really so crucial for this type of game, because really what we're doing is to decompose the moduli space we're working on according to these types of Stokes graphs. And just for each of the, say, patches or charts defined thereby, we need the coordinates, and well, just we need them to extend just enough such that, say, in the neighboring patch associated to different type of Stokes graph, there's another coordinates, and that we have an analytic change of coordinates between them. So this is here for this game the more crucial aspect. So therefore, I mean, of course, these are not new coordinates. These are coordinates that Andy et al. Have studied a lot, except that I would like to stress that perhaps a bit more attention than before can be devoted to these Fenchel-Nielsen type coordinates.
Right, so my question is precisely not about the coordinates. Usually in this wall crossing game, you have smooth interpolating functions in which you can express it in terms of locally defined coordinates that are jumping around, but there's still something global and smooth that interpolates that all together. I was hoping this function t might be of that sort. Maybe that's not clear in the story yet.
Well, the functions t again are a priori locally defined, but they do have in the examples that we study, they do always have analytic continuation basically to the whole modular space. So in this sense, they're global. But I mean, the crucial bit again is of course how they transform from chart to chart. I'm not sure. Maybe actually I had a difficulty understanding acoustically what you were saying, but I hope nevertheless to have addressed the question somewhat.
So sorry to interrupt the engaging discussion. So I think we need to start setting up our next talk. So perhaps probably we can keep discussing in the private discussion setting, and we also have a breakaway session after this in the evening, so we can discuss there further. Thank you, Jack, for this beautiful talk. We're going to set up for the next one now.
Thank you.
Let me set it up.
I need to kick me out.
I'm just.
Jessica, I think if you share your screen, it will override.
Yes. Francesca?
Yes.
Yeah, can you share your screen?
Yes.
Okay. I do not see it from my end. Okay. Yes. Okay, our last speaker for this for the first session today is Francesca Ferrari from CISA, and she's going to talk about quantum modularity of three manifold invariants.
Thanks. Thanks for the invitation also to speak at this virtual string math. So as you said, I will deal with quantum modularity of certain free manifolds invariants. And I can just a second. The talk is based on the different works, mainly the 3D modularity paper, work made in collaboration with Cheng, Chun, Gukov, and Harrison, and also other works with Gabriele Sgroi. And at the end, I will also mention a work in progress with Pavel Putrov that he already discussed yesterday. So I will just briefly describe a few other features of free manifolds invariants we are considering. So this works relies on the interplay of different branches of mathematics, number theory, where quantum modular forms arise, and also other objects I will describe during my talk. Low-dimensional topology, free manifolds, and in particular free manifolds invariants for closed, I will just consider closed connected free manifolds, plumped free manifolds, and the physics that is rooted in the 3D correspondence, and in particular describes different 3D theories, topological 3D theories, so Chern-Simons theory on one side, and supersymmetric 3D n equal to 2 theories that I'll describe later. Mainly, I will describe two invariants, WRT invariants, and the recently introduced homological blocks. And until at the end, I will quickly mention a few other invariants that seem to have also quantum modular properties. So I'll start with a description of modular forms to introduce then strong quantum modular forms and highlight the difference and similarities they have. Then I'll go into the topology side and describe the three manifolds I will considering WRT invariants and homological blocks, as I already mentioned. So let me start by defining a modular form. As you probably all know, a modular form phi of weight k multiplier system chi with respect to a group gamma that can be a discrete subgroup of SL2R is a holomorphic function phi defined from the upper half plane to the complex plane, which satisfies the functional equation written below, where I used the notation of a slash operator, in particular the weight k slash operator, which is defined here. And where, as usual, the action of gamma on H is given by fractional linear transformation. And from the practically all the talk, I will just take gamma to be SL2Z. Another thing I will use is what I call cusp form, which is basically a modular form whose Fourier expansion takes this form. And so it starts from positive integer n. And Q will be e to the 2 pi I tau, where tau is the object that lives in the upper half plane. Now, quantum modular forms have been defined by Zaguer in 2010, and even earlier in a paper with Lawrence. And they have a particular features. As I mentioned here, they're defined at the boundary of the upper half plane. So instead of being defined on the upper half plane as usual modular forms, they are only defined from the rational and I infinity, so the cusps of the upper half plane. Moreover, they're neither analytic nor gamma covariant functions. Why this is the case? Basically, since they're defined on the boundary of the upper half plane, the topology that they inherit from the action of gamma on the upper half plane is a discrete topology. So any form of analyticity or continuity will be vacuous. And moreover, they cannot be invariant function under the action of group gamma. Otherwise, if they would basically be trivial functions, since gamma acts on the cusps with finitely many orbits, and if you require covariancy under the action of gamma, you will practically obtain a trivial function. So here you can see the difference between quantum modular forms and modular forms. However, what he required in his definition is that the failure of this analyticity actually is a offset in a sense by the modularity. And what I mean by that is that so a quantum modular form of weight k and multiplier chi with respect to gamma is a function from Q to C, or if you want P1 Q to C, such that for every gamma, this function P gamma x has a better analytic behavior than Qx. So if you take the original the quantum modular form in X and subtract the modular transformed quantum modular form, what you obtain is a function that has some property of analyticity. And moreover, it's a cocycle on gamma. For all the cases that I considered in this talk, actually P gamma, this also called period function, is a real analytic function on P1R minus a finite subset of points. And I will also just restrict it to what are usually known as strong quantum modular form, which in this case is a function Q, which associates to each element X a formal power series over C. So that this identity actually holds between countable collection of formal power series. And again, all the examples that I'll considered below, I do not only associate a power series, but I can actually define a function Q, which extends globally to the whole complex plane minus the real line, but plus all the rational numbers. So in particular, you can imagine it as a function defining the upper half plane that leaks through the rationals into the lower half plane. And given this definition, you can see that there is a lot of ambiguity in extending this function from the real line, or actually from the rationals, to values in the upper and in the lower half plane. And we'll see how this ambiguity will play a role later. But first, let me describe you the first three manifolds invariants I consider, usually known as Witten or Reshetekin-Toric invariants. And it is defined as the partition functions of Chern-Simons theory on the free manifold M3. And here I'll just restrict to the gauge group SU2. It is defined more generally, but for my thoughts, this is what's sufficient at the moment. And as I mentioned, the level, this makes sense. There is a consistency quantization condition for K an integer. However, thanks to Reshetekin and Toric that defines these objects combinatorically using representation theory of quantum groups UQSL2, this definition actually extends to a function from the rational numbers. So instead of being a function of 1 over k, where k is an integer, it makes sense at any rational number point to a complex number. And moreover, you can even associate an asymptotic series that corresponds to the perdurative expansions around 1 over k at a certain saddle and 1 over k for k that goes to infinity. So this object was proven to be a topological invariant. And moreover, it was shown to be an example of strong quantum modular form by Lawrence and Xavier. A new homological invariant came into play a few years ago. It was defined by Gukov, Pei, Putrov, and Vafa in 2017. And the idea is rooted in this finite class of 6D n equal to 2,0 theory, where I will just mention the A1 case labeled by this Lie algebra on M3 times D2 times S1. Basically, compactifying this theory on different manifolds, I will obtain either a topological quantum field theory. Here, I'm going very quickly, but just to give you a flavor of what's going on. So I will get either a topological field theory, which is actually analytically continued 3D Chern-Simons theory on M3 when I compactify on D2 times S1, or a supersymmetric three-dimensional gauge theory, 3D n equal to 2 theory. And that is actually a coupled system. It's a 3D, 2D coupled system where the 2D is actually the boundary of this manifold, that is a torus, and is defined by a certain 2D n equal to 2, 0, n equal to 0, 2 theory or boundary condition. So given this setup, they considered the half index of this theory TM3, and they find it to be the also known as homological block, Z hat of tau. So basically, this half index, that is the supersymmetric partition functions on this space and with the given boundary condition, can be taken to be a new free manifold invariance, which is also, it's a nice Q series with integer power and integer coefficients up to maybe an overall Q power and coefficient. And that can be thought as graded Oriel characteristic of certain BPS sector Hilbert spaces of this 3D theory. Well, here I actually is the charge under a U1Q rotation, where here argument of Q, that is tau, is actually describing the rotation of the disk once you go around VS1, and J is the U charge of the U1R symmetry. To define it from a topological point of view, just from the free manifold, we consider plumbed free manifold. As also then, you might have already heard about this yesterday in Pavel's talk, where a plumbed free manifold is determined by a weighted simple graph, where V are the vertices of the graph, edges, and some framing coefficients that are associated to each vertex and will correspond, describe how to make a surgery of a link associated to this graph to obtain the free manifolds M3. And in fact, you can think of this graph also has a link where each node is, you associate to a link and not, and the edge will correspond to chaining to a not link. Moreover, this plumbing graph can be equivalently described by an adjacency matrix, where each node to which is associated the framing coefficients will correspond to a certain elements on the diagonal of the adjacency matrix, and the off diagonal will tell you if the nodes are connected or not. M, moreover, induces a non-degenerate symmetric bilinear pairing on the torsion of H1 of M3Z. And this, in the case I will consider here, B1 of M3 is 0, so the torsion is basically the co-kernel of M. Moreover, for the time being, I will restrict to the type of free manifolds that are weakly negative plumbed manifold. And this means that the inverse of adjacency matrix is negative definite when restricted to the subspace generated by high valency vertices. So in particular in this graph, the only high valency vertex is V1. High valency vertex corresponds to vertex of valency greater or equal to 3. And if restricted to subspace, this subspace is negative definite. This is needed in order for the definition they gave to give rise to a nice Q series or an isomorphic functions in the upper plane. In fact, Gugoff Petrov and define for a weakly, actually for a negative plumbed free manifold, and gauge group SUN, but here again I will just focus on SU2, the homological block Z at A of M3 tau that you can see here as contour integral. Well, here pi's are just the positive eigenvalues of M, sigma is the signature, alpha p are framing coefficients, and this integral here, in the case of I will consider, I will not even need a principal value, but I will just take the constant term with respect to y's of this integrand expression to obtain what is the homological block. Q again is e to by I tau, and y is given by e to by I z. The label you can see here is identified with elements of spin C structure modulo the action of the val group Z2. Moreover, the theta functions is given by this expression, and again, boundary conditions are given by spin C, and delta V is the degree of the vertex. Here you can see why the condition, the negative condition of M3 arises, otherwise this theta will be divergent. In addition, what they showed is that given a homological block, if I take the radial limit, so I take tau towards a root of unity, or sorry, tau towards a rational number, q to a roots of unity, and take these particular linear combinations of z hat p, what I obtain is Simon's partition function. Where here, everything the linking pairing are all determined by the type of free manifolds or plumbing. What we observed, and this Ringman, Burg, and Milas did in 2018, is that the quantum invariant z hat A is actually given by a linear combination of what is called false theta functions, up to possibly a polynomial and an overall Q power. These false theta functions are very similar to theta functions. However, as you can see, instead of summing Q to the certain quadratic form with all positive signs, I'm start taking plus and minus signs. These objects arise from holomorphic Euler integral of certain cusp forms. I will explain in the next slide what holomorphic Euler integrals are. For the moment, let me say that theta 1 is a cusp form, but it's a unary theta series of weight 3/2 that one can obtain from the Jacobi theta functions, just taking the partial derivative with respect to z. And as you can see, it is this form. Now, the morphic Euler integral of a cusp form can be defined as follows, where gt tau is equal to the Fourier coefficients of the cusp form I started with, and then take the exponent of q to 1 minus weight of the cusp form. So in our case, this would be n minus 1/2 q to the n, thanks to the fact that we have unary theta series with a certain quadratic form at the exponent. Here, I'm not introducing rationality. And I will obtain back false theta functions once I use as cusp form unary theta function. This type of holomorphic Euler integral arose from the theory of Shimura and Mani when they're considering a primitive of certain cusp form. In fact, for integer weight, they also have an integral representation that will appear again in a moment. First, let me mention that first false theta functions define quantum modular forms when we go towards rationals. When tau is taken, we take right limit towards the real line. And this fact, together with the connection between homological blocks and modularity invariants, allowed us to retrieve many topological information from free without knowing much about the free manifold, but just using the property of false theta functions. Now, the fact that the false theta functions define a quantum modular form must tell us that there is the action of a modular group of psi, even though psi is not modular, doesn't have a modular properties, at least not an apparent one. And however, if you remember the definition of quantum modular forms, I told you that we could have a globally defined function. So starting from a quantum modular form defined on the real line, on the rationals, we have a certain function that continues to the upper half plane, but something even in the lower half plane. So till now, I described what Z is. It's an holomorphic function in the upper half plane, and its radial limit corresponds to some to the WRT invariants on the line. However, I didn't mention at all what happens in the lower half plane. So is there something in the lower half plane? And in case, what is, even from topology point of view? It turns out that related to weakly Z hat A for weakly positive definite free manifolds. So the oppositely oriented free manifolds. So, well, from the Otsuki series, or if you want the Chern-Simons, perturbative Chern-Simons trivial flex connection, we know when we take k that goes to infinity, we have that the Chern-Simons partition function on minus M3 with level k has the same asymptotics as the Chern-Simons on the weakly negative definite free manifold, evaluated in the opposite level, minus k. So in particular, here you see how Q and Q inverse role. And another condition we have, though, is not that the asymptotics of two functions agree, as in general for quantum modular forms when we consider a function on the upper and the lower half plane. But in this case of free manifolds invariants, we also expect that to be a nice holomorphic functions with well-defined expansions and integral coefficients. So given these two constraints we have, we want to retrieve what is z hat A of minus m3 tau, given the fact that the original definition of z hat A was not possible to retrieve an Q series due to the divergence inherited in the functions in the integrand of the homological block. So to see what is on the other side, I have to introduce mock modular forms. A mock modular form f weight k is a holomorphic function f. Completion is a modular form that satisfies the functional equation. However, this function is a holomorphic function that doesn't transform as a modular form when I add a certain holomorphic Schiller integral of the cusp form, in my case, or more generally, holomorphic modular form, G, I obtain something that transforms modularly. This G is usually called the shadow, and is the cusp form I need to describe the non-holomorphic Schiller integral that I need to have something that transforms nicely under transformation. Now, as you notice here, down happens to non-holomorphic integral, the correction term that is needed and is equal but opposite to the correction term that is needed for f to have something modular, and is given by this integral that again is a period function like for modular form. So in particular, when I take tau that goes to the real line, I obtain a quantum modular form G star and a period function on the right side. So to connect to false theta functions, I need to introduce the non-holomorphic Schiller integral now in the lower S plane. As I told you, the false theta functions and the objects that appear with homological blocks for weakly negative lambda 3 manifolds are related to G tilde x plus I G, which I take the limit towards certain rational point x. I get the definition of get a quantum modular form. Now, what I'm telling you is that given the normomorphic Schiller integral, it's obvious in a sense, is the holomorphic Schiller integral on the side. I have the same quantum modular form from the other side. So it's leaking procedures I was describing at the beginning. To make this formally, you can see that these Schiller integrals agree to infinite order at any x, so that we have this asymptotics. However, as I told you, I can't consider z hat cannot be directly connected to this, which is a holomorphic function and have a nice Q series expansion even in the when I go to the upper plane. So I have to go back to the initial description of mock functions by illusions. He introduced them when he was analyzing the 20. He noticed that they have a certain distinctive features. In particular, they had infinite number of exponential singularities at roots of unity. What Griffin on Rowland and Choilim-Rhodes later showed is that actually they proved, still Ramanujan state this, noticed that there is a collection of weakly holomorphic modular forms, Gj, such that the f minus the Gj is bounded towards all cusps equivalent to xj. So in particular, if I have given a certain cusp, or the one under modular group considering, in order to remove the exponential singularity of x, I need to subtract weakly holomorphic modular forms. And I need a collection of them. One holomorphic modular form will not be enough if I have more inequivalent cusps. So given a choice of this weakly holomorphic modular form, what was proven is that F tau, my mock modular form, defines a quantum modular form by this. So taking the subtractions of this weakly holomorphic modular form and the radial limit of these objects, we obtain a quantum modular form. And in particular, this is the same, in a sense, quantum modular form that is defined by the limit of the holomorphic Eichler integral of the cusp form, G. So given a mock modular form whose shadow is a cusp form G and G tilde is its Eichler integral, then F and G tilde have the same asymptotic series at X in Q. So this is basically what we were looking for, and what we conjecture with Gukov and Harrison is that if the homological block Z hat for a given free manifold is given by a certain linear combinations of false theta function, then the oppositely oriented free manifold is associated with an homological block, which is a linear combinations of mock theta functions. Mock theta functions, that means mock modular forms whose shadow is a unary theta series. And as I mentioned at the beginning, the shadow is actually, and this cusp form is what gives rise to the false theta functions, and thus is the shadow of this also mock theta functions. This conjecture showed with different procedures. So in particular, we can, as I told you at the beginning, we have a lot of ambiguities when we try to extend the quantum modular form to the upper or lower half plane. In particular, I could add cusp forms to my mock modular form, and this will have the same shadow as marginal mock modular forms, yet will be a different object. How do you define Z hat? We propose sort of minimum choice. In particular, there are different techniques to get from to go from a false theta functions to a mock modular forms. One of them is through Rademacher sums, and that basically connects false theta functions to minimalists or another choice of theta functions that are actually the one also described by Ramanujan. There are also other works on this, and in particular, Gukov and Manolesco showed with the different techniques that follows more a definition through topology, that you can get exactly the sum of a mock modular form that we conjecture to have when M3 is a weakly positive definite. And also Cheng and Groy are also working on this and trying to modify the definition in order to regularize these theta functions that appear that are not convergent and make sense of the definition of homological for a weakly positive definite graph. So to summarize, given a certain homological blocks associated to a free manifolds, and here I'm only considering Seifert manifolds with free singular fibers. There are other works for other higher fibers, and we're also considering higher fibers and higher rank gauge groups. But here I'm only considering SU2 gauge group and free singular fibers Seifert manifolds. For these cases, Z hat is connected to a linear combinations of false theta functions, which appear as holomorphic Eichler integral of unary theta series, but are also a shadow of certain mock modular forms, which we conjecture to be related with Z hat of opposite-oriented free manifold. Particularly, when I take the radius of a false function, we get a quantum modular form related to WRT invariant. And for the mock, I will need a certain correction term to again get the quantum modular form and the corresponding WRT invariant. So before concluding, I'll also mention the work with Pavel, where we consider homological blocks for supergroups. In particular, here we mentioned the case of SU21, and free manifolds with trivial H1 for homology group in Z. In this case, Z hat can be similarly defined, even though, well, here the Weyl denominator of a of this super Lie group appears, and the theta function is now given by an indefinite theta function. So the integral is not anymore as easy as taking a constant term of this integrand expression, but in its definitions of, you need to define where this variable are, in which chamber to get a nice holomorphic functions in the upper half plane. And moreover, the invariant can be shown to be defined only for minus and inverse weakly copositive. And where these conditions arises from the fact that you want the invariants also to be invariant for different, when you apply Kirby moves on a certain Lambing graph, you know you'll get homomorphic free manifolds that are described differently by different Lambing graph. There is a certain redundancy you have to get rid of if you want to get a certain topological invariant. And what we observe is that for the homological block associated to free sphere, to S3, there is a single one, and you have this nice Q series associated to it, where the n is the number of positive integer divisors, and is in fact related to the weight 1 holomorphic Eisenstein series, E1 tau. These objects has been analyzed by mainly Bettin and Conray, but also Lewis and Zagier in 2010. And in fact, they describe other types, again, strong quantum modular forms, where if I take the radial limit of E1 tau minus the modular transformed Eisenstein series, I again obtain a period function, which has some nicer analytic property than the functions I'm started with, that is the Eisenstein series. And in particular, in this case, it extends to an analytic functions of a slit complex plane. Unfortunately, for this case of supergroups, in the case of more general free manifolds, like already Brisker homology spheres, at the moment we haven't been able to see yet a quantum modularity, but they're much more complicated objects, and the number theoretical literature is much smaller in these cases. So let me conclude by mentioning the fact that for free manifolds invariants, there have been many works on different type, always homological blocks, but for higher rank gauge groups, more complicated free manifolds. And it has been noticed that there's a connection between logarithmic vertex operator algebra, in particular singlet VOAs, with Z hat for the case of SU2 gauge groups and ciphered free manifolds with free singular fibers. In the case of homological blocks for supergroups, there are still many questions open. And while I say probably even not only for supergroups, but one interesting fact is that apart from the quantum modularity I described you, there are also other type of free manifold invariants, for instance, Kashaev invariants, Color-Jones polynomial, that are related to quantum modular forms. So in a sense, they appear to be natural in this context of low-dimensional topology. They turn out useful to describe topological information, and so they hint a hidden model structure. In, for instance, for the case of false theta functions, we can see this explicitly. But given the definition of quantum forms, what I also wonder is there a place where we can find our quantum modular forms? Are they only natural from the free manifold point of view, or are they much more common objects, what we know at the moment. So I stop and thank you for the attention.
Thank you, Francesca. Thanks so much for the excellent talk. I'm going to unmute everyone, and let's give a big hand to our speaker. Now, this is the time for questions. So I see there's a question from Edward Witten.
My question is mainly, does positivity of the 3 manifold mean something in terms of geometry, like positive scalar curvature or Ricci tensor or something?
You have to unmute yours. Francesca, you're muted. You need to unmute. Francesca, you need to unmute.
We can't hear you, Francesca.
Can you unmute? There's a. I send you an unmute request.
Thanks. Yes,
Okay.
I was just looking for the button. No, I'm not sure. I mean, for instance, the examples we consider of ciphered 3 manifolds, they basically the positively oriented 3 manifolds are given by the same plumbing graph with opposite framing coefficients. And this gives kind of a negativity or positivity condition. But,
so is it true that positive or negative manifolds have positive or negative curvature?
Mm-hmm.
Nothing else, so, but you know.
No. Sure.
What kind of, I might be completely on the wrong track, but when I hear your talk, you have an invariant that's defined at the rational points on the real line. Which it's defined when Q is the root of unity. And then you're trying to continue it away from the values of Q where it's originally defined. Naively, that would just give a holomorphic function of Q, maybe, or who knows where its singularities would be. But you seem to be in a setting where there are 2 different continuations. One is holomorphic in the upper half plane, one's holomorphic in the lower half plane. Is that
basically, basically, you have a certain functions, but let's say, let's take a certain function holomorphic in the upper half plane. In this case, what happens is, for instance, if I have a certain Q hypergeometric series expression of the function, formally Q vector to Q in and re-expand it in the upper half plane. In that case, in this case, as I described here, I get 2 different functions. This one, for instance, a false theta function, and another mock theta function.
So do
that's another side.
These functions have the same value when Q is a root of unity?
Yes. In the
Should we?
Pavel described.
There is another question by Mikola Didchenko. I'm going to read the question.
May also just the last question by Witten.
Oh, sorry.
One thing is, okay, this idea of continuing, let's say, but you cannot continue because both functions have natural boundaries on the real line. But the idea of flicking on the other side goes even back to the marker, where he was considering a modular form and trying to see what happens to the asymptotic expressions of these modular forms if I try to define it on the other side for Q equals to Q inverse. And if you, depending on how you go, you can use different techniques to go on the other side. You might even get a 0 on the lower half plane. So in particular with the Rademacher sums, you will have a modular form defined on one side of the plane and an expansion of 0 on the other side. I don't know if this helps, but it's just to explain.
Thank you.
Okay, there is another question from Mikola Doroshenko. I'm going to read the question. So can you state what is the class of 3 manifolds for which this modularity story works?
So the mock-false conjecture has been based only for 3 singular fibers ciphered manifolds. Now, depending on what you mean by the modularity story, in the sense, it depends a bit. If I increase the number of fibers, I will still obtain, for instance, for 4 singular fibers, I'll still obtain some type of false theta function. But now I'll have different weights, not only one I did here, but multiple false theta functions associated with shadows of different weights. And if you increase the rank, you're only asking what's the class of them. Then there are other works, for instance, a paper by Chung, Gukov, Sopengo, Park. They also describe the genus 1 toric manifold, and in that case as well, false theta functions appear. So there might be also the other side of the story.
Is there any other question? There is a question from Ali Shepard. I send you the unmute request. Can you hear me?
Yes.
Okay.
Thank you for the talk. Can I ask about the relation of this modularity story with the logarithmic VOAs that you mentioned on this slide? Mm-hmm. Is there, for example, what are some hints towards this connection that you could give?
Yeah, so we're working on it now with Chang, Chung, Bukov, Harrison, and Boris Fagin. And so what we already noticed in the previous paper is that in the case, again, of ciphered prime manifolds with 3 singular fibers, the logical block is related with the characters of singlet logarithmic 1p VOA. And moreover, there's also connections for 4 singular fibers, where you actually have pp prime logarithmic VOA singlet. There seems to be a connection to triplet as well from the ground, but we're still trying to understand how far this connection goes. So for which type of prime inputs and so on.
Are there any other questions? I think if there are no further questions, then I want to thank the speaker one more time for this excellent talk. And this is actually the end of our first session. And I want to thank all the speakers for their nice talks and everyone for this engaging participation. And now I'm handing over to Jeff. Thank you.
Thanks.
Thanks, Shajid. Sylvia, I've made you co-host.
Hi, thanks. I have a simple question. How do I see, how do I mute people? Maybe when I become a co-host, I understand.
You're co-host at the moment. If you look at the
Oh, yes. Oh, yes. No, I understand. Okay, just I found it. And the same when people ask questions, I should see their hand.
That's right. So Zoom floats people to the top as they raise their hand.
Okay, perfect. Thanks.
I just want to see if Yanghui is around. Yeah. Okay. I will make him co-host as well.
Yeah, hello. Hi.
Good, excellent. Very good. So we have about 12 minutes to the next session. So maybe Yanghui, do you want to see if everything works? You want to share your screen? Just make sure everything's going.
Sure. Let's see. Right.
Excellent.
That's all right. Now I'm trying to. How do I move this aside? Yeah, I guess I could just move this aside.
We can see your screen now as a presentation.
Yeah.
Okay, fantastic. All right, so we have about nearly 10 minutes before the next session starts.
Okay, I can get a coffee or something.
Yep.
Right.
still a couple of minutes, then we start.
No problem.
Zoom really takes the awkward silences to a whole new level.
Yeah, I know, because I'm not, one can't tell whether one is there or not.
Yeah.
But hi, Jeff.
Hi.
How's it going?
Yeah, good. I owe you a reply to your last email. I will get around to it. I think the answer to your question was yes, but
okay, yeah, no problem. Yeah, sure. Well, I wish I were in Cape Town in person.
I agree. It would have been great to see everybody. So let me quickly say that welcome to the next session. Our next chair of the session is Silvia Penati, and she will introduce the next speaker and take it from here. Silvia?
Thank you, Jeff. So I remind everybody that you can ask questions at the end of the talk, raising your hand and unmuting yourself, or I can unmute you, or just write the question in the chat and then we read it. So we start the second session with Yang-Yu He, talking about universities as big data or machine learning mathematical structures. Please.
Thank you very much, Silvia. Thank you very much for having me at this conference, albeit virtual. I wish I were there in person to see everybody. So I'm going to talk about some of the more recent works I've been doing in machine learning and its relevance to both the string math community and to the mathematics community at large. So let me just begin, really, this is sort of a historical note for the younger students about how this story really started. So, I mean, the story really started in 1984. Of course, as we know, the first string revolution, Green-Schwarz anomaly cancellation, and then the heterotic string of GHR in 84, 85. The one that I want to point to is this old paper of Candelas, Horowitz, Strominger, and Writ in 1985, which started this field, which we now call phenomenology. The point was, the two key points we want to take away from this is that, you know, the standard model gauge group embeds into E8. Now, this is just a group theory fact back in the days of quantum field theory. And then this E8 comes sort of for free from the heterotic string. And that's the first take-home message. And the second one from that is that the standard solution for the extra 6 dimensions in the compactification is that it is some Ricci-flat Kähler manifold. Of course, there are many, many other possible solutions, but this sort of became known as sort of the standard solution of compactification. It just so happens that mathematicians were independently thinking of a very similar kind of problem. So this really goes back to the history of Riemann uniformization. In complex dimension 1, we know there's a trichotomy classification of Riemann surfaces, basically into Ricci flat, Ricci negative, or Ricci positive. So a huge number of work over the centuries sort of trying to relate topology to algebraic geometry, to differential geometry, and to index theory of some form. So what mathematicians were doing was to try to generalize this picture, where this boundary case of complex dimension 1 is what we call Ricci flat or torus. And here is the sphere, and here are negative curvature beasts. And in complex geometry, in algebraic complex geometry, this Ricci flat case is this Kähler-Ricci flat case that I was referring to earlier. And these are Fano varieties, and these are varieties of general type. So this culminated in the 54-57 conjecture of Calabi and the subsequent proof by Yau, the Fields medal winning proof of Yau in 77-78, into the statement. The details of the statement is not so important, but the key is that there is an analog of the fact that Ricci curvature controls classes of curvature, controls topology of manifolds. Of course, you don't expect this to have high dimension in general. For Kähler manifolds, at least some kind of trichotomy theorem of such a type. So it just so happens, of course, that Scher and Yau were neighbors in 85, so they were the big people to talk to. So this is a quite fortuitous coincidence. And Philip tells me that it's the physicists who actually named this Ricci-Flag Kähler manifolds as Calabi-Yau manifolds. Okay, so this is just to set the background. So here came a sort of an early physical challenge to algebraic geometry. And this is, as far as I know, this is one of the very first precise questions that the physics community has ever asked the algebraic geometry community. So if you take the tangent bundle of the Calabi-Yau, has a natural SU3 structure. The commutant of SU3 is E6 within E8. And E6 at the time was a very interesting gut theory, right? Of course, now we're doing much more sophisticated things. You can use Wilson lines and discrete symmetries to break this, and some other version of guts to standard model. But that's another story, which I'll get back to very, very briefly later. But at least within this context, back in the day, the generation of particles and the anti-generations of particles were succinctly summarized in the 27 and 27 bar of E6. Now, this is just purely from group theory. But the beautiful fact of this algebraic geometric compactification scenario is that the 27 bar is associated with the H1 of the tangent bundle, and the 27 bar with the H1 of the cotangent bundle, which by Hodge decomposition is H21 and H11. Now we know there are 3 generations of particles, so this imposed a natural topological constraint of your internal manifold, namely Euler number is plus minus 6. Right. Of course, I'll mention later, this has been generalized to holomorphic vector bundles and so on, and I'll mention that, but at least back in the mid-90s, this was a challenge to the mathematics community. This is a very precise question. Are there smooth, compact, Ricci-flat Kähler manifolds, or threefolds, with Euler number plus minus 6? It was immediately seen that the obvious worked. The quintic manifold, this is sort of the first one you can do. In general, of course, a homogeneous S1 polynomial CPN is Yau of dimension n+1. That's dimension. The quintic is the Hodge number is 1, 101, and the Euler number you can check is twice the difference, which is minus 200. Minus 200 is certainly not plus minus 6. So as far as the, of course we can do better now, but back in the day, the quintic was simply not good enough for model building. Right? It was interesting for many, many other reasons for the string math community, but it was not good for model building. So to answer this challenge, sort of within I would say 20 years, in steps of 5 to 10 years, various collaborations have been trying to establish data sets just to sift through to see whether it is possible to create this answer, to address a particular manifold analysis question. Well, the first data set that was done was by Candelas, Amminge, Hübsch, Lütgen, Schumerick, and Berglund from the first 4 years after the 1985-86 period. And what they were focused on was this data set known as complete intersection Calabi-Yau manifolds. So just very briefly, what these things are, they're just natural generalizations of the quintic. Instead of having a single polynomial in CPN, you take multiple multi-degree polynomials in products of CPN, such that each sum, row sum, is one more than this embedding space. So that's the Chern class constraint. And such that the sum of these dimensions minus the number of polynomials is equal to 3. That's the complete intersection constraint. So this classification was very, very interesting in the mid-80s, and this became a central problem to string phenomenology in the first decade. So people like Dissler and Green and Ross were all working on this data set, and in particular on what's known as the Chern manifold. So it was very quickly realized by these guys that the problem is a finite problem that you can classify up to permutations and equivalences. You can classify all of this. And it was also very quickly realized that this classification is way beyond what can be done by hand. So very resourcefully, these guys turned to the best computer at the time, which was the CERN supercomputer. So they turned to the CERN supercomputer and then ran this, and they found 7,890 matrices. So these are 7,890 Calabi-Yau threefolds, compact smooth Calabi-Yau threefolds, and with 266 distinct Hodge pairs and 70 distinct Euler numbers. So this data, unfortunately, is lost in computer form. You can look for magnetic tape versions of this in Lutken's office or dot matrix printout versions of this in Philip's office. But luckily, this data we have now resurrected with Andre Lucas, Laura Anderson, and friends. So this is now, there is actually an ASCII version of this freely available. So, so that there we are. So 7,890 matrices by mid-1980 standards was, I would say, big data. Unfortunately, it's that you quickly notice that all of the Euler numbers were negative. So this is actually a biased set. So it's kind of interesting. But of course, people knew about mirror symmetry at the time already. So mirror symmetry maps H11 to H21, so and therefore maps Euler number to negative Euler number. So Philip, Monica, and Rolf then looked for perhaps a more balanced data set. And this became known as the hypersurfaces weighted P4. So this is another way to generalize. So I talked about the quintic, right? That's CP4. One way to generalize that is to take products of CPNs. Well, another way to generalize CP4 is to take weights, take weighted CP4 and to consider homogeneous hypersurfaces in that. So this was done in 1990, and then around about 8,000 manifolds were found. And this is a much more balanced data set with Euler number distribution from minus 960 to plus 960. So, right, so continuing on. So this is the really, really impressive work by Kreuzer and Skarka. Well, why stop at weighted projective space? Right? I mean, the most general weighted projective space generalization is a toric variety. And due to a theorem of Batyrov and Borisov, which says that, if you take the anticanonical divisor of a toric variety constructed out of a reflexive polytope, then that hypersurface is Calabi-Yau. So this works in any dimension. So in particular, if you can construct reflexive polytopes in dimension 4, then you will get a lot of Calabi-Yau manifolds. Just to give a picture of this problem is actually very, very simple, and it's remarkable that people don't know the general answer to this. So in dimension 2, there are 16 reflexive polygons. So what's reflexive? All that means is that there's one single lattice point, and every bounding surface, hypersurface, is one distance away. So you can check there are exactly 16 of these up to SL2Z. This was known to people, to the classical Italian school of algebraic geometry. People like Fano and Del Pezzo knew about this. So what these give us, but the Batyrov-Borisov theorem says, if you take the anticanonical divisor in the toric variety constructed out of this, so the toric variety here is complex dimension 2. If you take the hypersurface, homogeneous polynomial in these, then these are Calabi-Yau one-folds. So what are Calabi-Yau one-folds? Well, these are elliptic curves. So this gives us exactly 16 very distinguished elliptic curves. What is remarkable is that this is known, back in the late 19th century. Already in dimension 3, the answer is unknown to the mathematics community. So imagine how many polytopes can you write, polyhedra, that you can just do facets in polyhedra, the lattice polyhedra, such there's one single interior point, and every facet is one distance away from this. This is a problem, and then classify this up to SL3Z. You can state this problem to a high school student, and yet this is an open problem. And interestingly, this was solved by Kreuzer Skarka by brute computer search, and they found 4,319 of this up to SL3Z, right? So, you wonder what the next number is in the list, right? 1, 16, 4319. And next number, remarkably, is 473,800,776. And in fact, we don't know what the generating function is. I've talked to countless combinatorists, and nobody knows the answer to this. Howard Skarka had a paper last year which said that the next number is at least 185 billion. This is such a simple problem, and yet nobody knows what the answer is. But for Calabi-Yau construction is that each one of this, if you take a hypersurface, could potentially give a smooth compact Calabi-Yau threefold. And to get that huge number, this 473 million, Kreuzer-Skarke used 6-month running time of a dual Pentium SGI machine. By late 1990s technology, this was as best as it gets. So in this data set, you have suddenly your Calabi-Yau database went from like a handful to around about 16,000, now to 473 million with 30,000 distinct Hodge numbers. And interestingly, all distributed between minus 960 and plus 960. In fact, so far, no known Calabi-Yau, compact Calabi-Yau threefold has ever broken the record of 960, and we don't know why. It is a conjecture of Yau's that the topological type of Calabi-Yau manifolds is finite in every dimension. So we already see this in dimension 1, right? Because in dimension 1, the Calabi-Yau manifold of dimension 1 is just in the curve. So the torus, there's a single one topological type. But the general Yau conjecture is that this number should be finite in every dimension. Well, we know that number is at least 473 million dimension 3, but we don't know what it is. So in some sense, this really kickstarted the age of data science in mathematical physics and string theory. So it's not, here's something that I rip off from the internet. Experimental physicists have been ahead of us very much in sort of data science techniques. But as far as the usage of data science as a field in mathematical physics and in string theory in particular, you really should go back to these, 2 decades after the initial challenge, which is this very precise question to algebra geometry. So, of course, there's been countless works. I hope I've given enough credit here. Just data mining, in particular, the Kreuzer-Skarke database, right? This 473 million is huge. Even by today's standards, this is big data. So various collaborations all across the world. And I think many people here, like Ron and Miriam, and Jim Halverson and Brand and Franz and Vishnu, we're all data mining this 473 million. So you can see some of the summary of this in if you wish, in this booktube here. So here's a plot of the Euler number versus the sum of Hodge numbers. So mirror symmetry is left-right flip here. And my only contribution to this diagram, the black and white version is already done by Kreuzer-Skarke and Philip. You can see a printout version of this, a framed version of this in Philip Candelas' office. But my only contribution to this diagram is I colored it in. So this is a heat density plot of the distribution of the different Euler number Hodge pairs with respect to the number of different Calabi-Yaus per Hodge pair, right? You see, there's 473 million, but only 30,000 distinct Hodge pairs. So there's a huge concentration around about the 27 mirror, self-mirror threefold. There's about 1 million data points over here and very sparse elsewhere. So Wattie Taylor's done some nice work in explaining why this is empty. So a lot of these are elliptically fibered. So moving on, just to make sure that we're not searching through a null set, that indeed, there's a lot of these manifolds, that we can actually find something akin to the MSSM or some version of the MSSM. There's been a lot of work by the Penn collaboration, the Oxford collaboration. I should mention this beautiful paper of Anderson, Gray, Lucas, over in Party. So they actually did a scan of line bundle models on various sissies. And this is a nice takeaway home number. Around about 210 to the 10 give you, sort of exact MSSM spectrum. So this 1 in a billion is also very much in the spirit of the type 2 constructions of Dieter Lust and friends. So Philip believes that there should be some kind of a trickle-down mechanism that selects our universe within this vast expanse of possible compactification. So of course, that program, of course, became much, much richer with the growth of all of these things over the years. There's D-branes, M3G2, F3 fourfolds, and each one of them have different types of geometries and sort of explosion of landscape data. And of course, there's this famously quoted 10 to the at least 500 for the vacuum degeneracy of KKLT and Denef and Douglas. So in some sense, string theory trades one very hard problem, the quantization of gravity, by another very, very hard problem, and perhaps a richer, more interesting problem, which is how to look for the right compactification within this vast landscape of possible geometries and beyond. So where do we stand? Well, the good thing is, in the last 10 to 15 years, there have been, as I mentioned, there have been various large collaborations. But in addition, I should mention, there have been now beginning collaborations with mathematicians and computational mathematicians, especially with the SAGE Math project, the GAP, Bertini, Magma, Macaulay 2, and Singular projects, just to bite the bullet and compute these things by mapping through these databases. And a lot of this landscape data is freely available. So, if you're bored tonight, I welcome you to just go to the internet and just download them. They're about 1 to 10 gigabytes typically. So that's the good thing. The bad thing is that the generic computation is hard in the technical sense. So if you want to get into any of the nitty-gritty details of this computation, which I'm going to outline one of them in a minute, whether you're doing dual cone algorithms to do triangulation data, or for the toric varieties cases, or you want to do this generic algebraic variety cases, you have to put in Grosvenor bases. All of these are at least exponential, sometimes even double exponential running time with respect to complexity. So if you want to really scan through the Schaka database, it's already quite impossible. If you want to do that in the spirit of what was done in the Oxford collaboration, that's already quite impossible if you want to go through the thing. So one natural question is asked, could we borrow new techniques from the big data revolution? So here's a wild question. So the typical problem in string theory and algebraic geometry is some kind of input integer tensor to some output integer. The reason I say this is because we don't have analytic metrics. So a lot of the things with the first go, if you want to do any of these computations, is to get some kind of topological invariant, right? So back in the day, the Euler number was the one that was the challenge. This is some integer. The generalization of the Euler number, of course, is that you have Singer index, and etc. There are various other versions of this problem. But whatever it is, you have some kind of an integer tensor input to some kind of integer output, at least within this framework. And I will mention other kinds of inputs and outputs shortly. So the question one can ask very naturally is that can classes of problems in computational algebraic geometry be machine learned by some kind of AI, or can we machine learn the landscape? Now, I will be precise about what I mean by this. So this was a problem that I addressed in this paper back in 2017. It seems, experimentally, it seems so for many of these problems, for sometimes curious and sometimes more understandable reasons. It just so happens in 2017, 4 groups of my friends were all thinking about this problem independently. So it's kind of, or similar versions of this problem. But I think I've become somewhat of a fanatic in the sense that I really do think that one can machine learn the fundamental language of mathematics. And I will discuss that in a minute. So interestingly, let me just give you, I love this plot about the progress in string theory. So the first strings conference was 86. The first string Pheno was 2002. And then there was a string vacuum project, which sort of followed on the string Pheno from 2006 and 2010. And the first of this series is 2011. And 2014, this is probably my proudest contribution to the string community, is that my friends and I made sure that there's a string session at the Society of Industrial and Applied Mathematics Conference each year, starting from 2014. And interestingly, in 2017, there's a new annual strings branch of conference. It's called String Data. So everybody's welcome to attend that one as well. So let me just go back to this problem. So let me just go back and ask, what is a prototypical problem, right? So here's the one that machine learning tried to address. Now this is how I write numbers 1 to 0. If you ask a mathematical physicist, how does a machine recognize this? Well, being mathematical physicists, we'll ask, can you construct a clever Morse function? How about compute persistent homology, find topological invariants of these digits, right? These are possible solutions, but they're highly computationally inefficient. So what does Google do? What does your tablet actually do? What machine learns? It takes hundreds of thousands of samples, for example, from the MNIST database, and then just some I guess some poor teams of graduate students has to label all of these. And so here's the number 3, and I'll go back to this in a minute. So what is machine learning in a nutshell? So I'm going to give you, for this community, I'm just going to give you machine learning in 1 minute. So it started in 1957, surprisingly, and this whole game, and it started with the word perceptron, and it started in its early AI experiments. All this is that you're trying to imitate the functions of a neuron. So you define some activation function, okay, that takes some input tensor, and then you consider weights and biases. And typically this function is some sigmoid and tangent. So that's it, that's what a neuron is. And if you just have a single neuron, all machine learning is just nonlinear regression, right? So you just take some input and you check, you minimize some standard error or something like this, and you check against some validation data. But the magic of all of this is the emergence of complexity. Instead of considering a single neuron, you put this in a connected graph and then let the connectivity of this graph do the magic. In fact, there's a theorem that says even a single layered, two-layered feed-forward neural network with sufficiently large number of nodes can approximate any function. Right? So you can imagine, this is essentially like, you'd put more and more terms with your Taylor series. So that's all I want to say. So what's this got to do with the problem that we're trying to address? So what occurred to me was exactly this diagram, right? If you look at the digit 3, this in standard representation is a 28 by 28 matrix of RGB data. Each pixel, so this is 28 pixels by 28 pixels. Each pixel is some RGB data. Here, you can even put the data. This RGB data can be, here's grayscale, so just some number between 0 and 1. But if you think about what a complete intersection is, it's very similar. For example, if you look at this thing, well, an algebraic geometer will tell you this is CP1 cross CP1 cross CP1 cross CP1 cross CP1 5 times cross CP2 cross CP2 cross CP2, and you're doing the complete intersection of 8 homogeneous polynomials of these homogeneous multi-degree within this, and that gives you Calabi-Yau manifold. But this matrix is nothing. Why not think about this as this pixelated image, right? With some kind of RGB. I've colored green as 1 and red as 2, but that's not so important. The point is that this matrix can be computed to have H11 equal to 8. The proper way to do it, of course, is to use everything that Bourbaki has taught us, right? You establish Hodge composition, get an Euler sequence for the subvariety, and induce a non-exact sequence in cohomology, right? And you do this, and you compute this, and you for this case, you return the number 8. But this computation is at least double exponential running complexity. If you want to do this properly, if you want to establish coordinate basis, these things, Sage Math does some versions of this. For the quintic, you would compute this, but in general, it's very, very difficult. But why not just associate this image to the number 8 and then train on samples? We have the CC data sample to train from. So it kind of works very nicely. So in these works, and in the original work of 2017, and then with my student Kiran, and then with Vishnu and Challenger, we tried the CC classification. There's also a paper this morning which used the Google Inception neural network to redo this calculation to almost 100% accuracy. So the point is that you let the machine look at 20% of your data and learn the patterns in it in some mysterious way, and then predict the remaining 80% and to see how good you get. And 80, 90% accuracy with 0.9 confidence is very good. So similarly, you can do this. So another game that I played with Sanjay Lee was that, is it possible to distinguish elliptic fibrations within the Calabi-Yau data set? And then very quickly, within 30% training, you could get almost 100% accuracy. So all of this, of course, is bypassing very complicated theorems of Oguiso, Collar, and Wilson about how to actually check what elliptic fibration is. So there have been a lot of more success stories in algebraic geometry. Fabio Rula did this beautiful work on genetic algorithms for computing bundle cohomology. And by the way, he wrote this nice monograph on data science applications to string theory. And of course, there's a whole program of Jim Halvorson and Brent Nelson and Cody Long and Northeastern just to do the machine learning of the Kreuzer-Schacke data. And then Brody and Konstantin Lucas did exact formula conjecture formulation of exact formulae for line-bound cohomology for various surfaces. And and various other things. So here with Anthony Ashmore and Bud Overett, we tried actually machine learn Calabi-Yau metrics. And this machine learning actually improves the sort of the state of the art algorithm, which is a Donaldson algorithm for numerical Calabi-Yau metrics by almost 2 orders of magnitude. And so too, you can apply this distinguishing quadratic standard models from line-bound cohomology. And in fact, the machine learning has now become a standard program within the string pheno community. But my interests are actually much more general. But I just like to point out, Koji Hashimoto has this very radical, very beautiful proposal that ADA-CFT itself is a Boltzmann machine, that itself is some kind of machine learning paradigm. So this is very interesting. With successes in algebraic geometry, why stop there, right? Why not look at other problems? So with the number theorist Min-Young Kim, what we looked at is, well, why not look at representation theory and group theory, right? So here's another database, the GAP. Oh, by the way, GAP does not stand for, it's not the genes company. GAP stands for Groups, Algorithm, and Programming. It's a huge collaboration that catalogs around about 10 million finite groups, the first 10 million finite groups, as well as, of course, the full character data for the sporadic groups, right? So 2 of the questions we asked was, if I give you a Latin square or a Sudoku, when is the Latin square the actual Cayley table, a multiplication table for finite group? Right. So if you train some kind of a support vector machine to do this classification problem, you could actually, even at 20% of training data, you could start predicting, up to 95% accuracy when some random Sudoku is actually a group table. Well, let's take this one notch further. Can we distinguish finite simple groups from the space of possible groups? So from some initial problems, from some initial experiments on groups of small order, this seems to be the case. And of course, you're bypassing, back in the day, if you want to decide whether some group is simple, you got to, use all this Silov and Noether isomorphism theorems. But the idea is not to use these and just to train on this data and see what is possible. So I hope, and this is work in progress, that it is possible if you actually plot the Cayley table in the space of finite groups, there is some kind of hypersurface that separates the simples from non-simple. If I could find that hypersurface, that could be actually a very, very interesting problem. So this is in progress. Well, so from geometry, we went to representation theory and group theory. Well, what about combinatorics and graph theory? Well, that seems suggestible that this is also possibly machine learnable. So last week I had this paper with Yao, which is to test whether a standard machine learning algorithms can learn finite simple graphs. There's a Wolfram database around about 10,000. So their standard graph theoretic problems is a graph cyclic, is a graph planar, is a graph, is the genus of the graph greater, equal, or less than 0? Does there exist Hamilton or Euler cycles? And all of these problems, many of these problems are MP hard, right? This I must emphasize. And the Hamilton cycle problems, so that's cycles which traverse vertices exactly once. The Euler one is that traverse edges exactly once. The Hamilton one is known to be MP hard. But instead of trying to do this, we'll just train it on some distribution of these, and then try to predict, with what confidence can I say that this is possible. So apparently, for to decide whether a graph is cyclic, you can reach 0.95 confidence. This is quite good. And what about spectral bounds? Spectral bounds meaning, what about lower and upper line distribution of eigenvalues of the Laplacian of the graphs? There you get R squared also up to 0.9. This is good. And there's of course our favorite problem with Yao, which is there's a notion of Ricci flatness for finite graphs. is it possible to start creating more of these Ricci flat graphs? So at least within the known Ricci flat cases, a support vector machine can decide, and also boosted decision trees can also decide to 0.9 confidence. So this is kind of nice. This is a very fun project to do, because you would think that combinatorics is also very much amenable to this kind of study. And then similarly with my collaborators, what about quiver mutation? Of course, this is known as the cyber duality in the field theory community. Can you know whether two quivers are cyber related or cluster mutation related? And within the set that we tried, this is also doable to high confidence. Well, why stop there? Why not train your network to try to recognize whether there's even order reflection symmetry, right? This is something else we've done earlier this month. And yes, and that is also a very much doable problem. What about distinguishing 3 points, whether certain functions are actually 3-point functions of a CFT? Yes, also good. Fourier coefficients and conformal block presence, also very good. And you can see this also very nice work of Kurtendorf and Savary on distinguishing symmetries. I should emphasize that, of course, we're not solving the traveling salesman problem. That is just not possible. That's an NP hard problem. What we're doing is to stochastically solve it, right? We can't say that this is there's a graph that solves this problem, but at least I can tell you that 95% of the time it will solve this problem. So that's what we're basically doing. So we've gone from string theory to algebraic geometry in general, to representation theory, to combinatorics. Well, one would naturally imagine that this kind of thing would go wrong somewhere. And one would imagine it would have go wrong in number theory, right? So if you try, and number theory is always very, very hard problem. So, and that's exactly what we played. So in these two works, how about just try to predict the primes, right? You can try a supervised machine learning problem of the following type. 2 goes to 3, 2, 3 goes to 5, 2, 3, 5 goes to 7. Or even better, try a fixed window size as you go on whether there's a yes, no answer to predict whether the next thing is a yes or a no, right? And very reassuringly, any neural network I've ever tried has always given confidence 0.00001. That you truly suggest that the prime numbers are randomly distributed. I expect the same for the zeros of the Riemann zeta function. If you try to do something like this, will be very, very hard. You're better off just using the prime number theorem. Just use the x over log x to have an estimate rather than to have this kind of exact match. So of course, if you can do it, I mean, I'm not saying there's no theorem that says this is not doable, but if you can find a neural network that does this, you will break every bank in the world. Well, if a frontal attack on the primes is difficult, what about intermediate problems in number theory? Well, we tried on descent d'enfant, right? This comes from of course, this is Grothendieck's esquisse on studying the absolute Galois group. This is a analytical problem which tries to study algebraic number theory. So maybe you would hope that the behavior for neural networks is marginally better than 0.00001. And so we tried this problem of adjacency of descent d'enfant to try to predict the transcendental degree of the descent. And okay, it's marginally better. It's about 0.2, 0.3. Well, why stop there? What about the Birch-Swinnerton-Dyer conjecture? Well, here, this is doable because there is actually a database done by John Cremona, known as the LMFDB. I think this is very much liked by much of the quasi-modular forms community within this community. This is the database of elliptic curves and modular forms and L functions. So basically, what we did here, so these guys are Laura Alessandretti and Andrea Baronchelli are data scientists. So I had explained to them the mathematics and they explained to me the data science. What we did was machine learning and topological data analysis on this data set. This data set is around about 10 million elliptic curves. So, and what we were doing is trying to learn whether it's possible to predict the relevant quantities in the BSD conjecture. So I'm not, there's no time to get into the details of this. Getting Weierstrass to the rank of the elliptic curve is a completely random prediction yet again. So this is a very badly behaved problem. But if you want to do some kind of regression on the Shafarevich number, it's actually not that bad. So I think I'm out of time. So let me just summarize here. So the idea of this program is, I believe, useful both for physics and for mathematics. In the physics, you can use, this kind of neural networks as classifiers of the landscape data, and importantly to use as a predictor to estimate results which are clearly beyond current computational power. Right? So this is why the string phenol community likes this so much. In mathematics, I've been thinking about, I guess, a very, to me, seems like a very profound question. How is and how could AI do mathematics without knowing any mathematics? It seems algebraic geometry over C is doable, combinatorics and representation are doable because they're dealing essentially with some matrix manipulation, right? Algebraic geometry C, all problems in algebraic geometry over C are dealing with co-kernels and kernels of matrices. So here is a small mapping of a hierarchy of difficulty of machine learning. Numerical analysis is the best. Algebraic geometry over C is great. Luckily, algebraic geometry over C is probably the favorite field for string theory. Combinatorics algebra is slightly worse, and the most difficult one, as you can imagine, is number 3. So my friend Boris, who is the professor of logic, says, you're doing syntax without semantics, which I think is a wonderful way of putting this. But it's not entirely, one could imagine that we're right now, what we're doing is the AlphaGo stage of mathematics, and we hope to go into the AlphaZero stage, is what I call the Tversky stream of automated theorem proving using machine learning. And similar papers of such a nature have actually appeared. So there's a paper, Riemann et al. In Nature last year, where they use this autoencoder, which they call SciNet, which finds heliocentrism from only the positions of Mars. So this is kind of interesting. You don't feed nothing, and it's generating some basic laws. Similarly, in Lampon-Charton last year, where they're trying to machine learn symbolic manipulation in mathematics, where they could actually get new integral identities that things like Mathematica could not do. So I think I'm exactly on time. So thank you very much for your time. Let me.
Sylvia, I think you're on mute.
Sorry, yes, thanks.
Okay.
Are there questions?
I see hands raised, but I don't know how to address them.
Yeah, I don't see the person.
Yeah, I can help there. First one is by Shriyar Sikandar. I'll unmute you.
Thank you. It was just a suggestion for the Birch and Schwinnert-Dyer conjecture, and so you're trying to solve, or you try to teach the computer the most difficult version of Birch and Schwinnert-Dyer.
Yes, that's right. I'm doing the strong version. That's right.
So is it possible to try to teach the computer, a simpler version of Birch and Schwinnert-Dyer where it just predicts if the rank is 0 or non-zero? Because there's a conjecture that half of the elliptic curves have rank 0 and half of them have rank bigger than 1. So it would be nice if computer can say something about that.
Right. Actually, sadly, the one we tried, in the Cremona database, the ranks were all 0, 1, 2, or 3, and there's a tiny bit of 4. I know the ranks can go up to like 20 or something, but within this database, they're very small rank. Yeah. So even within there, a simple classification of, if you want to try to say, let me give you the Weierstrass coefficients of the elliptic curve. So this is just, the They're just 6 of these integers. And then I train it to predict whether the rank is 0 or not. Even that is a random prediction, sadly.
I see. Okay. So
that, I mean, it was in some sense that was reassuring, somewhat reassuring, because it's a hard problem.
Absolutely. So I think the other easier one would be that one starts off with an elliptic curve and then looks at its quadratic twists. So basically, essentially look at the family that, I mean, an example of that would be the original family of Birch and Swinnerton Dyer, which is y squared equals x cubed plus d. And if
that's
you just
good suggestion. Yeah, I should. That's a nice suggestion. I should try to extract families of the elliptic curves to see how the rank. I'll probably end up getting some kind of analytic formula for rank with respect to such twists. Yeah, but that's a good suggestion. I don't know. I should try it.
Okay, I see other 2 people who raised their hand, but I don't see who. I'm sorry, Jeff, but I cannot see who is rising.
Okay, no worries. The first up is Greg Moore. Greg, can you unmute? Yeah, there we go.
I finally was able to unmute, yes. Yeah, so I had 2 questions actually. One is, do you think these techniques could say something about point group symmetries of even unimodular lattices of high rank?
Oh gosh, if there is a good representation of such, I guess you can put in. So, well, what do you envision? You feed in these matrix, these lattices as matrix generators?
Well, I was deliberately vague. I mean, there are lots of ways that one could try and formulate a precise question, but
I would imagine.
I was just wondering if that was on the table as the one of the subjects of these investigations.
I'm not thinking about this, but absolutely one should try it. One can see where in this hierarchy that problem lies, because my hierarchy so far doesn't have any sort of lattice. So I would guess the lattice of sort of somewhere lattice type of problems will stay somewhere here, somewhere between combinatorics and number theory.
Right, because we know the number of even unimodular lattices, which are interesting for a number of reasons, but we know the number is also growing at a terrific rate. So, reminiscent of the growth of Calabi-Yau. Okay, my other question is a more general one, and is perhaps more pertinent to applications to string landscape. And what happens if you're training on data that turns out to be wrong?
Wrong in what sense?
Well, I mean, supposing you look at 10,000 pictures of a cat, but it's really a dog.
Yeah, well, then there's no way out of it. If you originally feed in something that's biased or wrong, then it will constantly bias it.
So this could be important for the string vacuum project.
That's right. That's right. We need
some large class of the constructions are actually wrong for some reason.
That's right. That's right. So then you must, for example, for the SISI data set, when we train it with Hodge numbers, we know those Hodge numbers were correct because they've been computed by other means, and the idea is to predict the thing.
Yeah, exactly. The algebraic geometry is obviously very solid, but I mean, for the other questions.
Yeah.
Okay. There is another, yes, I see, yes.
Can I just follow up on Greg's question quickly before we go to the next speaker?
Okay. No, there is another, yes, there is another question for him, which is this one. Yes, unmute.
Yeah, can I just follow up on what Greg asked? And suppose in your 10,000 pictures of a cat, some substantially large subset of the pictures are incorrect. So I guess my question is, how susceptible is the algorithm to noise in your training set?
Well, it certainly depends on what neural networks you're using. So a lot of the stuff that I've been using is supervised machine learning, which assumes that the labelings are correct. There is, a vast field of unsupervised machine learning, which the whole purpose of that is to try to extract sort of inherent patterns. So there are various things. There's generative machine learning. So, but within the supervised framework, you definitely want your labels to be correct. But there is unsupervised ones which does exactly pattern recognition without any input from the user, so to speak. So we should try that as well. And for example, a perfect problem would be try unsupervised learning on prime distribution or something like that. Could it recognize x over log x? And I think that it can do. So that it can probably do very, very well.
Okay, great, thank you. There's a question.
I think wait, there is still another question.
Yes.
By Chris Krylova. Yes.
Yes, hello. Thank you for the talk. That was great. I have two questions. I'm kind of related. The first one is, from what I understand, your work that you've mentioned is mostly computational. Is that correct?
Yes.
Okay, so then the second question is, what efforts do you have in terms of trying to derive it mathematically, like expand a mathematical framework? Because a lot of the algorithms that you mentioned, especially the ADS CFT related to Boltzmann machine, it's not a huge leap predicting that they're related, considering that they're both based off of partition functions. So what efforts are there to actually prove it mathematically and have a proper basis for it?
Good. That's a very good point. So one of the things that we've been trying to do is that, if you ever get a network that, say a 30% training is getting 100% accuracy, then you know that this is not just some kind of stochastic result. You could actually start conjecturing something. And then this was done by, in particular, in this paper of, there may be others, but there's a particular one that let me try to point to this, in this paper of Brody, Konstantin Lucas, and also I think by Magdalena Laforce, which they did exactly that. They tried line bundle cohomology of finding, computing cohomology even for line bundles on varieties is very, very difficult. You can do it on products of projective space by some kind of a Kuhn formula, but even if you have just like a hypersurface and you want to do a line bundle on that, it's already so crazy. But on surfaces, they were able to get 100%. And then so they were able to say, well, let's conjecture that this is actually the correct formula. So then they went back and beat themselves and chased exact sequences. And that was shown to be exactly correct.
Okay, that's great. And also in terms of, because a lot of the algorithms are not really precise too. I mean, the machine learning community also struggles developing these. So how does that help the other way, not going from machine learning to string theory, but for example, from string theory to machine learning?
There's actually a lot of crossover between physics and machine learning community. So I guess Google and Microsoft hire a lot of theoretical physics PhDs. So recently, I think last year there was I think it was the first kickoff conference by Microsoft. It's called Machine Learning Meets Physics. And so they want to learn techniques from us as well to understand more analytically what a lot of these neural networks are doing. I think one name that comes to mind is this guy called Taco Cohen, where he uses gauge symmetries. He has a physics background. He uses gauge symmetries to, I think, try to build gauge symmetries into his neural networks to improve certain convolutional neural networks.
Okay, but this is still mostly computational, it's not mathematically proven.
There is a sub-community there that tries to prove precise conjectures about neural networks. For example, the universal approximation theorem, and that's actually a theorem.
Okay. Okay, great. Thank you.
Are there other questions?
I see Andy Nitsky.
Yes, please. I will unmute you. Okay, you can ask the
Hi.
question.
Hi, Andy. Hey, how's it going?
Good. How are you? Thanks for the time.
Good to see you.
I just have a question. It's exactly on this slide, actually. You mentioned this thing of machine learning the Calabi-Yau metric, which improves Donaldson's algorithm by 10 to 100 times. So what does it mean to say it improves it by 10 to 100 times?
This is just computation time. So
so you get the same answer, but 10 to 100 times faster?
Yeah. So the reason that the Donaldson algorithm is so expensive is because, I mean, this was just tried on the quintic, and then you need to generate all the sections for higher degree, and then they grow exponentially. And then you have to try to sample the points, and then try to write down this huge sum over all of this over these high sections, and then optimize over these. So what we did was to take just a slight bit from a higher section degree for the section, and then machine learn the rest of them. So it bypasses the actual computation of trying to sum over the sections of all this large number of points. The reason we know it works is because you can check, right? You can always check whether your Calabi-Yau goes to zero curvature at the end.
I see. So you're saying it's about as much Ricci flat as the one you've gotten from Donaldson's, but you get it much faster.
That's right.
I see.
I think there's an upcoming work by Lara and James and Fabi on just trying to predict, forget about any algorithm, just try to predict G mu from the points. I'm looking forward to see what the result may be for that.
Okay, any other question? We can maybe take one more question. Okay, if not, let's thank the speaker again. So I will unmute you all.
Thank you.
And we can move to the next speaker in 5 minutes.
Hi, Sarah. You have co-host privileges.
Sarah.
Hello. Yeah.
Just share your screen. Hi.
Yes.
Okay, great. We see your slides.
Yeah.
Yep, perfect. Okay, maybe we can wait 4 minutes, 3-4 minutes to start.
Okay.
Okay, what do you think? Well, maybe we can start.
Sure.
Okay. So next speaker is Sarah Harrison talking about the spectrum on M04 via Liouville theory. Please.
All right. Thank you very much to the organizers for inviting me to speak, and to all of you for showing up virtually for my talk. Today, I'd like to tell you about some work in progress that I'm doing with two of my colleagues at McGill, Alex Maloney, a professor there, and a postdoc, Tokiro Numasawa, who will be leaving us in a few months to go to MIT. So today, I'd like to talk about the following very specific question, which can be mathematically stated as, what is the spectrum of the Weil-Petersson Laplacian on M04, which is the moduli space of genus 0 Riemann surfaces with 4 punctures? And before I tell you a bit more what this question means and how we're going to approach it, I'd like to start with some general broad motivation about why we're interested in this kind of question, asking this kind of question. And so from both, if you're both a physicist or a mathematician, there's a lot of interesting structure in understanding dynamics on moduli spaces. For example, just a few examples I thought of in physics, moduli spaces appear in string theory, for example, in low dimensional compactifications where the ground state is a wave function on moduli space, as well as a number of special BPS solutions in supersymmetric theories. And more generally in mathematics, spectral theory on manifolds is a very fascinating and intricate subject with connections to a variety of fields. So one such specific example of the kind of connections between fields that exists is a relation via a formula called the Selberg trace formula between eigenvalues of the Laplacian on a Riemann surface and the lengths of geodesics. And this is a very specific example of a more general phenomenon which has applications to geometry of various types, hyperbolic geometry, arithmetic geometry, as well as special functions in number theory and quantum chaos. So we're interested in exploring some of these types of connections on more complicated manifolds, that is, manifolds which are moduli spaces of Riemann surfaces. And specifically in this talk, I'm going to talk about our work using techniques from Liouville theory to study the geometry of moduli spaces on Riemann surfaces. So Liouville theory is a very interesting quantum field theory. It's conformal, it's irrational, and it's been studied for several decades by a very, very long list of people. And I've listed just some of them here. I'm sorry if I forgot to list you, but a lot of people have done a great amount of important work on this theory. And it's interesting for us, specifically because it has a deep connection to the geometry of Riemann surfaces. For example, in physics, if you want to quantize gravity in 2 or 3 dimensions, they involve integrating over moduli spaces of Riemann surfaces if you're in 2D, or quantizing the geometry of Riemann surfaces in 3 dimensions. And so Liouville theory is relevant for low dimensional quantum gravity from its connection to the geometry of Riemann surfaces. And finally, another set of work that people have done, which has motivated us, is recent work relating quantum gravity to ideas in quantum chaos. Perhaps the recent interest in this started with a paper of Maldacena, Schenker, and Stanford, but there are many other papers involving the study of specific systems in holography or quantum black holes and connections to the physics of chaos. And in some of these systems, moduli spaces play a special role. So I'll just mention 2 examples. One has to do with work done by Assad, Schenker, and Stanford, where they computed the path integral of Jakob-Teitelbaum gravity, which is a 2-dimensional theory of quantum gravity, and which involves integrating over moduli spaces of bordered Riemann surfaces. in order to show that this theory is dual to a random ensemble of quantum mechanical systems, as well as very recent work in explorations over averaging over moduli spaces of 2D CFTs to draw a connection to gravity in ADS3. And these kind of cases are of note because their spectra are known to be chaotic. So we're not going to do anything so specifically connected with quantum gravity today, though we are motivated by the connections between quantum gravity and chaos. But we're going to kind of consider a toy model and ask the question which is, can we see physics of chaotic systems by studying the motion of a quantum mechanical particle moving on M04, this moduli space of Riemann surfaces with 4 punctures? Okay, so that's a kind of a summary of our general motivation from a variety of directions. And here's the plan for the rest of my talk. So first, I'll give a brief review of Liouville theory and its connection to the geometry of Riemann surfaces. So this is a very detailed subject, and I'll just give sort of the basics of the results of this connection. And then I'll present the main object that we're going to use to study the spectrum on this moduli space, which is a natural metric which you can define, known as the Weil-Petersen metric. And then in the main and maybe most interesting part, I'll present our preliminary results on computing the spectrum of this metric. We're not going to do it exactly or analytically at all. We're going to use numerical techniques using an approximate form of the metric. But nevertheless, I'll be able to show you some results about eigenfunctions and eigenvalues of our approximation to the metric. And finally, I'll end with some extensions we would like to work on and open questions. Okay. So because our technique is going to be coming from two-dimensional CFT and Liouville theory, I'll just start with a review of Liouville theory. So it's a 2D quantum field theory which has the following action of a single scalar field with this potential, this exponential potential. And it's actually a conformal field theory where the central charge is commonly parameterized by a variable q, such that you can write it as 1 plus 6q squared, where q is this b appearing in the exponential plus 1 over b. And this conformal field theory has a continuous spectrum. So it's kind of interesting in comparison to other conformal field theories, which we can solve to a high degree, such as the rational conformal field theories, which have discrete spectrum. Liouville theory is notable because we know so much about its correlation functions, but it's kind of the canonical example of an irrational CFT that we can study. The primary operators are in the theory are vertex operators, which have a conformal dimension, which is related to this charge q in the following way. So the dimension, if you write the dimension delta as alpha times q minus alpha, and let alpha be q over 2 plus ip, that tells you the dimension of the primary operator. And p is a variable that's commonly referred to as the Liouville momentum. And the full quantum theory can be characterized by the set of endpoint correlation functions of these primary operators. And we know a lot about how to compute these correlation functions and their symmetries in the theory. So there's a beautiful connection between the quantum Liouville theory and the geometry of Riemann surfaces. And I'll start by describing the connection in the semi-classical limit when you take the central charge to infinity, or alternatively, this b variable to 0. So in this limit, if you appropriately rescaled the Liouville field phi, it obeys the classical equation of motion, which I have written at the center of the slide, that's known as Liouville's equation. And this equation was studied by mathematicians as far back as Poincaré, I think, who showed that a solution to this equation on a Riemann surface with certain boundary conditions at a number of punctures on the surface furnishes a unique constant negative curvature metric on the Riemann surface, where the metric takes the form ds squared equals e to the phi dz squared, where z is a complex coordinate on sigma. And you can have different boundary conditions at these points on the Riemann surface if you choose different dimensions of the primary operators in Liouville theory. So today I'm going to be talking about punctured Riemann surfaces. And in Liouville theory, punctures correspond to primary operators with Liouville momentum set to 0. But you could also consider cone points or holes with geodesic boundaries, which correspond to a different choice of Liouville momentum for the primary operators. So this is a connection to classical hyperbolic geometry of Riemann surfaces, coming from the semi-classical limit of Liouville theory. But you can also move away from the semi-classical limit and study the quantum theory, and this should tell us something about so-called quantum geometry of Riemann surfaces, which is also a very interesting subject, which I won't say much about today. So today we're going to focus on kind of the simplest case for us to study, though we may eventually like to study different, more general moduli spaces of Riemann surfaces. But today we're just going to focus on genus 0 Riemann surfaces with 4 punctures. And so I'd like to review a bit about the geometry of the moduli space M04 of these Riemann surfaces. So there are many kinds of ways to parameterize the moduli space of M04, but I'm going to focus on a specific one, which will be useful for the computations that we want to do. So, so let me describe the moduli space M04 by a single complex coordinate, x, which is the cross ratio coordinate, defined in terms of the locations of the 4 punctures by this equation z1 minus z2 times z3 minus z4 over z1 minus z4 times z2 minus z3. So this will specify a point in moduli space up to conformal transformations which preserve this cross ratio coordinate. So once we specify a value of x, we specify a particular Riemann surface, which labels a point in M04. So here I have a picture of a typical Riemann surface, sigma 04, in the moduli space, the locations of these 4 punctures. And here I also have drawn on the picture this, this circle, which is a geodesic on this Riemann surface. This is with some length, which I'm labeling L sub s. This is a minimal geodesic in the S channel of the Liouville theory on this Riemann surface. And it's also common to parameterize the moduli space by coordinates which are given by the length of this geodesic and some twist coordinate around this geodesic boundary that you specify when you glue 2 pairs of pants together to form this Riemann surface. These are known as Fenchel-Nielsen coordinates, but we're not going to use those today because it turns out to be much more difficult to use our methods to compute the metric in those coordinates. So, so I just want to show you, discuss a bit more about the cross ratio coordinates on moduli space. So if we define the cross ratio in the following way, it takes values in the complex X plane. And there are a number of symmetries of the moduli space. These symmetries act on the cross ratio coordinate by anharmonic transformations, and the generator of this group, the generators of this group are given by taking x to 1 minus x and x to 1 over x. And here on the left side, I plotted the cross ratio coordinate, the complex plane, and half of the fundamental domain for these anharmonic transformations acting on the cross ratio coordinate. So the whole fundamental domain is the area where you take this shaded region and also reflect it across the red line. But I'm plotting half the fundamental domain because it turns out that we're going to solve the Laplace's equation on only half the fundamental domain, using the fact that there's a symmetry about this red line of the moduli space. And it turns out we'll also find it convenient to use a different coordinate, tau, which we can define in terms of the cross ratio coordinate as I times this ratio of elliptic integrals of x. So now tau takes values in the upper half plane. And in fact, the moduli space M04 is just a piece of the upper half plane of the tau coordinate. So the tau coordinate is a multiple clever of M04. And the fundamental domain for the group of anharmonic transformations on X in the tau coordinate is plotted in the shaded region here. So these anharmonic transformations become modular transformations of the tau coordinate for some modular subgroup of SL2Z. So one reason why we'll find the tau coordinate useful is that things like conformal blocks, which are multi-valued in the cross ratio coordinate, are single valued in tau. Okay. So now I'd like to talk about the metric on moduli space, which we want to study. So there's a natural symplectic structure on M04, which I'll call omega Weil-Petersen. And it turns out this also arises naturally in physics in a number of ways. For example, as I mentioned earlier, the 2D path integral of JT gravity, as well as quantizing SL2C turns Simon's theory on a Riemann surface. And this symplectic structure leads to a Kähler metric on the moduli space known as the Weil-Petersen metric. And this is the metric for which we want to study Laplace's equation on M04. So there's a theorem due to Zograff and Takhtajan that the Liouville action is a Kähler potential for the Weil-Petersen metric. In general, we can't compute this metric exactly, but because of this relation to the action of Liouville theory, we can use techniques developed from Liouville CFT to get a very accurate approximation to the Weil-Petersen metric, which is what I'm going to discuss. So first we have to discuss how we can compute this action of Liouville theory in order to derive the metric. So since we're studying Riemann surfaces with 4 punctures, we have to analyze the path integral on a Riemann surface with 4 punctures, which can be expressed as a 4-point function of primary operators in the theory in the following way. So I put the 4 primary operators at the points 0, 1, x, and infinity. And this 4-point function is given by integral over operators of some internal dimension delta times some 3-point coefficients and a conformal block, which depends on delta, the dimensions of the external operators, and the cross ratio. And in this expression, I've set the deltas of the external operators all to c minus 1 over 24, which corresponds to the fact that we're studying punctures at the 4 locations of the external operators. So we're going to study this 4-point function in the semi-classical limit when we take c to infinity or the value q squared to infinity. And in this limit, the path integral behaves as an exponential to the minus q squared times the classical action. And the classical action has an expression in terms of a 3-point function action between 2 external operators and an internal operator, minus some so-called classical conformal block, which comes from the fact that the capital F, the full conformal block, exponentiates in the semi-classical limit. So in the classical limit, since q squared is going to infinity, it's convenient to rescale the dimensions of the operators we're working with by a factor of 1 over q squared. So I'm going to write these expressions in terms of a new dimension that I define as little delta, which is the original capital delta divided by q squared. And in the case of punctures, this little delta becomes 1/4. So the dimensions of the 4 external operators will have little delta 1/4, and then the internal one will have dimension 1/4 plus p squared. So in the semi-classical limit, the path integral will be dominated by a saddle point at some particular value of this internal dimension, little delta sub s, which I'm parameterizing as 1/4 plus p sub s squared. And this dimension is determined by the saddle point equation, which is just setting the derivative of the classical action with respect to p to 0. And this value of an internal momentum, saddle point momentum p sub s, has the physical meaning as the length of the minimal geodesic in the S channel, which is the geodesic I drew on a picture a few slides ago. So the length of this geodesic is related to p sub s by L sub s equals 4 pi p sub s. So our method for studying the metric is to use a semi-classical expansion around the saddle point to approximate the Weil-Petersson metric. So I'm going to show you how this works first near the boundary of moduli space in the cross ratio coordinate. So there's a boundary of moduli space when you take the cross ratio x to 0, which is like taking the point z1 and z2 very close together, or z3 and z4 equivalently. And in this case, the minimal geodesic just goes towards this boundary. So the length of the minimal geodesic goes to 0 because you're bringing 2 points on one side of it to 0. So this internal saddle point momentum goes to 0. So we can expand the classical action around both x equals 0 and p equals 0. So there were two, as I showed on the last slide, there are two contributions to the action. There's this 3-point function contribution and the classical conformal block contribution. And here you see the expansion of both of them near x and p equals 0. So just expanding to order p squared in both of these expressions and plugging them back into the formula for the classical action, we can derive the saddle point equation by taking the derivative of these expressions. And you see that it takes the following form. And this equation has a solution given by p sub s going like pi over minus log x bar plus 16 log 2. So this is the solution for the saddle point momentum near this boundary of moduli space. And now if we want to get the metric near the boundary, we just plug in the solution for p sub s and evaluate the action as a function of the cross ratio coordinate. And then we take two derivatives of it to get the metric. And we find that the metric near the boundary moduli space takes the following form. It goes like 8 pi squared over x bar log cubed of 2 to the 16th over x bar. And this computation actually matches a computation by Wolpert for the Weil-Petersson metric near the boundary and moduli space. Okay, so things like the conformal block expansion in the cross ratio coordinate only have a radius of convergence of 1. So this isn't going to be good enough for us if we want to analyze the spectrum of the Laplacian on M04. We'd like to do much better to get some kind of accurate computation of eigenvalues. So instead of analyzing the saddle point equation in the x coordinate, we're going to use a much better approximation by working in a new variable called q of x, which is defined as e to the pi I tau, where tau is this ratio of elliptic integrals of x that I presented earlier. So the idea to use this coordinate was promoted by Homological when he was discussing solution or computation of conformal blocks in Liouville theory. So conformal blocks converge extremely rapidly in this Q variable. Q takes values in the unit disk and they converge, and it converges everywhere except for small neighborhoods of around the boundaries of moduli space. So instead, we'll analyze the saddle point equation in the Q variable. And a method of doing this is we can define an expansion parameter, which I'll call epsilon, as pi over this log of this ratio 2 to the 8th over q bar, which happens to appear all the time in the same form, such that the saddle point equation becomes the following. It goes like minus 2 pi plus 2 p pi over epsilon plus a sum power series in powers of p plus expansion coming from the Q expansion of the conformal block. So the terms that I've underlined in blue, they both come from the expansion of the 3-point function. In principle, these coefficients, they're a sub n, they're known. They come from Taylor expanding some product and ratio of gamma functions. So we can compute them up to any order we'd like. And this order Q part, which comes from the Q expansion of the conformal block, we can compute it via recursion relations due to Homological also up to any order that we'd like. So expanding the saddle point equation in this way, we can make an ansatz for the saddle point momentum, which is some power series in epsilon, and solve this recursively in order to get a solution for P sub s. So here are some expressions for the approximation to the metric at different orders in this epsilon and Q expansion. So for example, if we only take the leading order in the conformal block expansion and expand up to epsilon to the 8th order, the metric has the following form on this top line in the epsilon expansion. And if we take leading, we can get corrections to this by expanding the conformal block to higher orders and powers of Q. So the expression is simplest if I only keep leading order in epsilon and order Q squared in the conformal block expansion, it takes the following form about in the second expression. So using this technique and enough time, computing time to expand just the conformal blocks to as high order as we'd like, we can approximate the metric up to our desired accuracy. And again, the power of this method is the fact that the expansion in the Q variable is rapidly convergent almost everywhere in the unit disk. So this is the method that we use to compute the metric in this dual epsilon and Q expansion. And now we'd like to check how accurate our computations are at a given order in this expansion. And so there are multiple kinds of checks we can do. So I'm showing you here our numerical computations compared with exact results for two quantities. First of all, the volume of the moduli space, which was shown in the third column, as well as the geodesic lengths at certain values of the cross ratio, which are known analytically. So in the first two columns, I've computed I show you the computation of the cosh of 1 over the geodesic length at cross ratio values x equals 1/2 and x equals e to the pi I over 3. These values are known exactly to be 3 and 7/2. And then I show you our numerical computation of this quantity at a number of different orders in the epsilon expansion, keeping only up to order Q squared in the conformal block expansion. And you see that it already gets to be pretty accurate, like up to 0.1% by epsilon to the 7th. But if you go extremely high, like epsilon to the 60, it becomes extremely accurate. And in the final column, we compute the volume of the moduli space given our metric. This volume is known exactly to be equal to 2 pi squared, which is approximately 19.7392088. And you see the numerical computation of the volume given our metric. And by the time we get to epsilon to the 60, it's accurate up to 4 decimal points. So this gives us some confidence about how accurate we expect our metric to be once we start computing things that we don't already know the answer to, like the spectrum of the Laplacian. Okay, so in this final part of the talk, I'd like to present some results that we have, preliminary results we have for solving Laplace's equation using our expansion of the metric. So, using our approximation in this epsilon and Q expansion, it's easy to write down Laplace's equation. And what I'm going to show you are results for the solution of this equation on the half fundamental domain, so the shaded region that I presented earlier in the tau plane, where we're going to impose Dirichlet boundary conditions on the boundary of this region. And this will capture the totally anti-symmetric sector of solutions to this equation. There are also other solutions that you would get by imposing other boundary conditions. But these are the simplest to solve, so we started with this case. And the way we solve it is using Mathematica's ND eigensystem function, which basically discretizes the fundamental domain with some mesh size, and numerically solves this equation. And another check on our results is we'd like to see that if we get to a suitably small discretization size and then change it to be even smaller, that our eigenvalues are roughly stable. And we find that the first eigenvalues were stable up to 0.01% when we decreased our mesh size. Okay, so what we can do is we numerically solve this equation. We can find the eigenvalues, which I'll present in a moment, as well as the eigenfunctions. So it's kind of cool to look at a visualization of some of the eigenfunctions in the tau plane. And here I show you just some pictures from our numerical results of these eigenfunctions. The ground state on the left, the I believe 5th excited state and 40th excited state here. Okay. So we also would like to study the statistics of the energy eigenvalues of the Laplacian. And one way we can measure this is by looking at something called which I'll call the adjacent gap ratio, which is defined as the difference between the nth and n plus first energy eigenvalue divided by the difference between the nth and n minus first eigenvalue. And so on the left, I plotted a histogram of this distribution for about the first 100 eigenvalues of the Laplacian and compared it to some probability distributions which arise from some known ensembles. So the purple, red, and blue lines are from 3 different random matrix ensembles, and the gray line is coming from just a Poisson distribution if the eigenvalues were totally independent from each other. I'm not sure this plot says anything very conclusive about which random matrix ensemble these eigenvalues might come from, but it does seem to show that they're certainly not Poisson. And on the right hand side, I have a plot of the average of this adjacent gap ratio as a function of the first n energy levels, where the energy level is plotted on the x-axis and on the y-axis is average for the first n of them, as well as, again, a comparison to some known distributions. And it looks like the average is maybe approaching what you would expect from random matrix in the Gaussian orthogonal ensemble. Though I don't want to say anything definitive about this. A second thing we can compute once we have a spectrum of energy eigenvalues is something known as the spectrum form factor, which probes the nature of the spectrum. In particular, it can probe whether the spectrum is characteristic of, say, a chaotic system versus an integrable system. So the spectral form factor is basically just the magnitude of the partition function squared. And on the left-hand side, I plotted the spectral form factor as a function of t on a log-log plot. For those familiar with the terminology, this seems to show a characteristic dip, ramp, and plateau, which was maybe first given the names a few years ago in a work by a large number of authors on black holes and random matrices, who studied the spectral form factor in random matrix theories and showed that it has this typical pattern in the case of chaotic eigenvalues. And on the right-hand side, I plot a linear plot of the spectral form factor. And we see that there's approximately linear growth in this region that I've fit with a red line, which is characteristic of eigenvalue repulsion in a spectrum. So again, the results from these plots, they contain the first about 100 eigenvalues of the Laplacian, computed numerically with a conformal block expansion, but only up to order q squared. Okay, so those are all the preliminary results that I'd like to show you. So I'd just like to end with some extensions and open questions that we'd like to explore. So the main summary is the following. We've initiated a study of chaos on moduli space, which is in fact quite an old subject and a very rich field in mathematics. But I think what we are adding here is the idea of using techniques from physics and conformal field theory, particularly Liouville theory in the case that we're looking at, to study this problem. And there are a number of directions that we can investigate further. For example, on M04 particularly, we could try and study the spectrum of geodesic lengths and perhaps verify something known as a Gutzweiler trace formula, which relates the density of states in a quantum system to classical periodic orbits. We can also try extending what moduli spaces we're looking at. The simplest way seems like, instead of considering punctures, to look at something like cone points, and more complicated than cone points would be geodesic boundaries, or generalized to other moduli spaces, such as a torus with one hole, or MGN in general. So the motivation for studying a moduli space with one boundary is that, well, one piece of motivation is that you can imagine that in ADS3 gravity, there are a class of solutions known as BTZ black holes, and you can imagine that there are solutions for BTZ black holes where there is some interesting geometry behind the horizon, such as a Riemann surface with one boundary, and use the quantization of the moduli space of this Riemann surface as a model for the microstates of a BTZ black hole. So there's a paper written about this by my collaborator, Alex Maloney. But more generally, we're just interested generally in the problem of quantizing gravity on the general moduli spaces of Riemann surfaces and understanding connections with quantum chaos. So that's all I want to tell you today. Thanks very much for listening.
Thank you very much for this excellent talk. So let me unmute everybody so we can thank you all together. Okay. Let's okay, are there questions? Yeah. First of all, from Sergey Gugov, please, I will unmute you. Yeah.
Hi, Sarah. Thank you for a very nice talk. I have two questions. One is certain aspects of the moduli space M04 are related to Penlev-6 equation. So one question is if there is a connection to tau function of Penlev-6. And second question is if there is any connection to physics of SU2 gauge theory with 4 fundamentals in 4 dimension for the n equals 2 theory.
Sarah, are you muted?
Yeah. No, it doesn't seem to be muted. Sarah?
Oh, sorry. Somehow I think I accidentally muted myself. I think the answer to both is I don't really know. For the second one, why are you asking about the question connection to, sorry, what did you say? SU2 with four fundamentals?
Oh, yeah, if we think about class S type construction
I
on
see.
this
Yeah.
Riemann surface, we naturally get 4D and SU2 theory with 4 fundamental flavors.
I see.
And tau parameter is tau of prepotential in Seiberg-Witten solution and necross of partition function. So that's the reason for the second question.
I see. Yeah, we haven't thought about that at all. So I don't know. I guess you could think of our eigenfunctions as wave functions on the moduli space, but we're with a very specific Hamiltonian, which is the Laplacian. And I'm not sure of a physical system where we can embed that setup into something like what you're discussing.
So are you happy with the answer? You want to say more? Okay, so maybe we can move to the next question by Shirayan. So let me unmute you. Yes, please.
Thank you. Shariar, just.
Sorry.
I just had so do you know what is the curvature of this metric that you're defining? If it is constant everywhere, or even if it is not constant, is it negative everywhere?
It's the metric on the moduli space.
The Weil-Petersen metric.
Mm-hmm. Yeah, it's not constant, but I haven't computed the curvature. I suppose we could. But again, yeah, we won't be able to compute it exactly because we don't have an exact expression for it.
Okay, so the reason why I was asking this is the following. In the standard case or in the classical case, when you look at the Laplacian coming from the hyperbolic metric, which you know is constant and curvature 1, in that case, there was a conjecture of quantum unique ergodicity. So you've already mentioned quantum chaos, but there's a slight generalization of that to quantum unique ergodicity, and it was very important in mathematics, and the person who solved it got the Fields Medal as well. So I was just wondering, so to formulate quantum unique ergodicity, you need your metric to have negative curvature everywhere, not constant, but just negative curvature everywhere. So if the Weil-Petersen metric does have negative curvature everywhere, that it would be a natural question to ask if the Laplacian actually the Laplacian with the Weil-Petersen metric actually satisfies a quantum unique ergodicity or not.
I see.
Second is, so I'll just ask quickly. Again, in the classical case, the eigenfunctions of the Laplacian are very special functions. They're called mass forms.
Mm-hmm.
And they're very important in automorphic theory. So have you looked at the automorphic theory of eigenfunctions of your Laplacian? Well, not your Laplacian, but the Weil-Petersen Laplacian.
Yeah, I mean, that would be great, but
So
I don't think.
The reason why I asked this, the picture that you showed of the functions, I tried to copy down the slide number, but there were no slide numbers. But you had a
I think they'll be posted eventually, the slides.
Okay.
So
you had a really nice picture of the eigenfunctions, and they look, I mean, this is obviously very in the upwavy. They look very much like graphs for mass forms, especially something called the nodal sets of mass forms. So I believe these eigenfunctions would have very nice automorphic properties as well.
Yeah, that'd be fascinating to study. Right now, we just have numerical solutions for them. So at this point, I think the most we could do with respect to automorphic properties is some kind of numerical analysis. But you can imagine trying to study that given the sort of expansion of the metric in some kind of analytic way. But it might, I mean, I imagine it might not be very obvious in the kind of form that we're able to work with. But I would imagine it's something more complicated than mass forms because the metric is way more complicated than just like a hyperbolic metric on the upper half plane.
I mean, which would mean they're more interesting as well.
Yeah, yeah. Thanks. That's that's a great point.
No problem. Thank you. There's another point, but I think I can ask that later in the breakout room. Other people should get a chance. Thank you.
Sure.
Okay, so let's move to the next question by Richard Terriberry. I will unmute you. Please.
Oh, hi. Yeah, thanks. I was just wondering whether you had an explicit bound on the error for your approximations of the Weil-Petersen metric.
We haven't tried to compute anything like that yet, mathematically, but that's a good question to look into.
Yeah.
Yeah. Right now, we just kind of have this preliminary, these preliminary results for. I mean, we have this method of expansion, but we haven't analyzed like the error of these quantities.
Okay. But cool. Okay, cool.
Yeah. Sorry. Yeah.
No. That's fine. It was a lovely table of known results versus approximations, but I was like, oh, but how do we know? But
yeah.
But cool. No, that was nice talk. Thank you.
Any other question? I don't see any other question. Okay, so I think we can stop this session for today. Let me thank once again Yang-Gui and Sarah for their excellent talks. And people now may want to move to the discussion session, and we will reconvene tomorrow for the next set of talks.
Thanks, Sylvia. I am currently assigning people to breakaway sessions. There will be 2 sessions as usual for 2 rooms, one for session 1, the first 3 speakers, and one for session 2. The speakers are automatically put into their respective rooms, but if you have a particular preference, please do send me please do send me a private message. And I will open the rooms at 7 p.m. local time, and I'll leave them open for an hour before which we'll close the after which we'll close the session for the day. So if you send me your preference, I can assign you now.